uh, Spring Cloud architecture. Here you can see general Spring Cloud architecture. Spring Cloud provides tools for developers to quickly build some of the common patterns in distributed systems. For example, configuration management, service discovery, circuit breakers, intelligent routing, microproxy, control bus, one-time tokens, global locks, leadership elections, distributed sessions, cluster state. Here you can see Spring Cloud architecture highlights. Service discovery. In cloud, applications can't always know the exact location of other services. A service registry such as Netflix Eureka or a sidecar solution such as HashiCorp Console can help. Spring Cloud provides discovery client implementations for popular registries such as Eureka, Console, Zookeeper, and even Kubernetes built-in system. There's also a Spring Cloud load balancer to help you distribute the load carefully among your service instances. API gateway. With so many clients and servers in play, it's often helpful to include an API gateway in your cloud architecture. A gateway can take care of securing and routing messages, hiding services, throttling load, and many other useful things. Spring Cloud Gateway gives you precise control of your API layer, integrating Spring Cloud service discovery and client-side load balancing solutions to simplify configuration and maintenance. Cloud configuration. In the cloud, configuration can't simply be embedded inside the application. The configuration has to be flexible enough to cope with the multiple applications, environments, and service instances, as well as deal with dynamic changes without downtime. Spring Cloud Config is designed to ease these burdens and offers integration with version control systems like Git to help you keep your configuration safe. Circuit breakers. Distributed systems can be unreliable. Requests might encounter timeout or fail completely. A circuit breaker can help mitigate these issues, and Spring Cloud Circuit Breaker gives you the choice of 3 popular options: Resilience 4J, Sentinel, or Hystrix. Tracing. Debugging distributed applications can be complex and take a long time. For any given failure, you might need to piece together traces of information from several independent services. Spring Cloud Sleuth can instrument your application in a predictable and repeatable way, and when used in conjunction with Zipkin, you can zero in on any latency problems you might have. Testing. In cloud, you get extra points for having reliable, trustworthy, stable APIs, but getting there can be a journey. Contract-based testing is one technique that high-performing teams often use to stay on track. It helps by formalizing the content of APIs and building tests around them to ensure code remains in check. Spring Cloud Contract provides contract-based testing support for REST and messaging-based APIs with contracts written in Groovy, Java, or Kotlin. Here you can see IoT, mobile, and browser is connected to are connected to API gateway. Actually, IoT, mobile, and browser interacts with API gateway, and API gateway interacts with microservices, service registry, and config server. Service registry interact with distributed tracing, microservices, and config server and API gateway. Config server interacts with microservices, service registry. Microservices interacts with service registry, distributed tracing, config server, and API gateway. Distributed tracing interacts with service registry and microservices. Here you can see the most important projects divided into categories. As you can see, the Spring Cloud contains many sub-projects providing integration with lots of different tools and solutions. It is easy to lose track, especially if you are using Spring Cloud for the first time. In accordance with the principle that one diagram might express things better than 1,000 words, here we are presenting the most important projects divided into categories as shown in this diagram I'm presenting here. Here Spring Cloud config, Spring Cloud Zookeeper config, Spring Cloud Console config, Spring Cloud etcd config, Spring Cloud Kubernetes config, and Spring Cloud Kubernetes config, and distributed configuration. Spring Cloud Eureka, Spring Cloud Zookeeper Discovery, Spring Cloud Console Discovery, Spring Cloud etcd Discovery, Spring Cloud and Spring Cloud Kubernetes Discovery in Service Discovery, Spring Cloud Hystrix, Spring Cloud Ribbon, Spring Cloud Feign, and Spring Cloud Soul in intercommunication, Spring Cloud Sleuth, Spring Cloud Sleuth Zipkin, and Spring Cloud Sleuth Stream in tracing, Spring Cloud Foundry, and Spring Cloud AWS, Spring Cloud Function, and Spring Cloud Connectors are in Cloud Platform Support, Spring Cloud Stream, Spring Cloud Bus, Spring Cloud Stream Apps, and Spring Cloud Dataflow are in Messaging and Integration, Spring Cloud Contract, Spring Cloud Security, Spring Cloud Task, and Spring Cloud Cluster are in Others. Here you can see a kind of complete architecture diagram of a Spring Cloud. Spring Cloud is a brand new web framework by Pivotal team. Its main feature is to simplify the deploying process. Spring Cloud contains a set of well-functioning and lightweight microservice components based on Spring Boot. The key characteristics of Spring Cloud are as follows: service discovery management, service fault tolerance, service gateway, service configuration, load balancing, and messaging. There are also well-tested and mature components in terms of bus and service tracking. This figure shows the sample complete architecture diagram of Spring Cloud. Eureka implements the automatic registration and discovery of microservices in Spring Cloud. Soul is used for dynamic routing and request filtering. Ribbon is a client-side load balancing based on HTTP and TCP that gets a list of services from the Eureka registry. Hystrix is a fuse that improves the system's fault tolerance. Turbine is a tool introduced to monitor microservice clusters. Fan integrates Ribbon to provide declarative HTTP API to clients. Spring Cloud Config provides a unified configuration management for Spring Cloud framework system and provides supports for the server, config server, and the client config client. The role of the Spring Cloud Bus is to connect the service nodes with a lightweight message broker such as RabbitMQ and broadcast the communication between the dynamic information of the configuration file and the service. Spring Cloud Sleuth integrates Zipkin to implement monitoring link analysis of microservices. Hystrix and Turbine Turbine are connected to Soul proxy and gateway. Fault tolerance is passed from Hystrix and Turbine to Soul proxy here and gateway. Ribbon is connected to Soul proxy. Load balance is passed from Ribbon to Soul proxy. Here you can see gateway, Soul proxy, and Soul proxy or Eureka client. Gateway interacts with Eureka server. Service calling is passed from back and forth between gateway and Eureka server. Ribbon interacts with a Fain client. Eureka server interacts with microservices and find client here. Register find is pass back and forth between Eureka server and microservice and find client here. Microservices interacts with microservices here. Find clients are passed from and to between microservices. Microservices and find clients interact with config server and Spring Cloud bus. M-service communication is passed from and to between Spring Cloud bus and microservice and fade clients. Config server interacts with GIT repo. Unified configuration is passed back and forth between config server and GIT repo. Spring Cloud interacts with Spring Cloud Sleuth and Zipkin. Monitor request and analysis request is passed in between Spring Cloud Sleuth and Zipkin and Spring Cloud bus. Now we are focusing on IoT. As an example, we can consider this code segment. Here we are considering domain in creating edge service using Spring Boot, in building IoT applications using Fauna and Spring. Well, edge service will consume and process health vitals. Let's create a record having a basic health vitals of an individual. Now we are focusing on mobile. Now we are focusing on browser. Now we are focusing on platform, CloudFoundry, etc. Services and applications will work well in any distributed environment, including the developer's own laptop, bare metal data centers, and managed platforms such as CloudFoundry. Here you can see pivotal platforms architecture. Imagine you have here basically we are considering Spring Cloud microservices at pivotal platform here with this architecture. Imagine you have multiple microservices running on different machines in multiple instances. It seems natural to think about the tools that help you in the process of monitoring and managing all of them. If we add that our microservices are created based on the Spring Cloud framework, obviously seems we should look at the pivotal platform. Here is the figure with platforms architecture. Here, although the pivotal platforms can run application written in many languages, it has the best support for Spring Cloud services and Netflix OSS tools, like you can see in the figure here. From the possibilities offered by Pivotal, we can take advantage of 3 ways. Pivotal Cloud Foundry solution can be run on public IaaS or private cloud like AWS, Google Cloud Platform, Microsoft Azure, VMware, vSphere, OpenStack. Pivotal Web Services hosted cloud native platform available at pivotal.io site. PCF Dev, the instance which can be run locally as a single virtual machine. It offers the opportunity to develop apps using an offline environment with basic services installed like Spring Cloud Services, SCS, MySQL, Redis databases, and RabbitMQ Broker. If you want to run it locally with SCS, you need more than 6 GB RAM free. As a Spring Cloud Services, there are available Circuit Breaker, Hystrix, Service Registry, Eureka, and standard Spring configuration server based on GIT configuration. Here you can see IoT, mobile, and browser interact with PCF router. PCF router interacts with Cloud Controller, PCF UAA, and API Gateway. API Gateway interacts with PCF router, PCF UAA, SCS Service Registry, and Spring Boot apps. Here SSO is passed back and forth from between PCF UAA and API Gateway. Cloud Controller is connected to Spring Boot app. Deploy or scale is passed from Cloud Controller to Spring Boot app. PCF UAA interacts with the PCF router, API Gateway, and Spring Boot app. AOT 2 is passed from and to between PCF UAA and Spring Boot app. Here you can see a Spring Boot app, and here you can see inside it below it Eureka and Hystrix Circuit Breaker and Ribbon Load Balancer. Here you can see Spring Boot app, and here you can see Spring Cloud Stream, Eureka, and Hystrix Circuit Breaker. Here you can see Spring Boot app, and here you can see Hystrix Circuit Breaker, Ribbon Load Balancer, SCS Service Registry interact with API Gateway, and Spring Boot apps, and databases, and service message brokers, and log analysis. Here Spring Boot apps interacts with SCS service registry, databases, message brokers, and log services, and MCF PCF metrics. And PCF metrics interact with Spring Boot app, SCS service registry, databases, message brokers, and log analysis. Here Spring Boot app is connected to databases. Service binding is passed from Spring Boot app to databases. Here Spring Boot app is connected to message brokers. Service binding is passed from Spring Boot app to message brokers. Here Spring Boot app is connected to log analysis. Log and metrics are passed from Spring Boot app to log analysis. Here log analysis is connected to here, and here analytics insights is passed to pivotal tracker. Pivotal tracker is connected to JIT. Code is passed from pivotal tracker to JIT. JIT is connected to concourse. Delivery is passed from JIT to concourse. Concourse is connected to PCF router. Code push, canary, red block are passed from concourse to PCF router. Here you can see microservices. Here you can see standard tier of private applications in Azure Spring Apps reference architecture. The following diagram represents well architected hub and spoke design addresses spoke design. Here in private application means internal applications deployed in hybrid cloud environments. Private applications, the following list subscribes the infrastructure requirement for private applications. These requirements are typical in highly regulated environments. Subnet must only have one instance of Azure apps. Adhere to at least one security benchmark should be enforced. Application host domain name service records should be stored in Azure private DNS. Azure service dependencies should communicate through show with service endpoints or private link. Data at rest should be encrypted. Data in transit should be encrypted. DevOps deployment pipelines can be used, for example, Azure DevOps, and require network connectivity to Azure Spring Apps. Egress traffic should travel through a central network virtual appliance, NVA, for example, Azure Firewall. If Azure Spring Apps config server is used to load config properties from a repository, the repository must be private. Microsoft Zero Trust Security approach requires secrets, certificates, and credentials to be stored in a secure vault. The recommended service is Azure Key Vault. The name resolution of host on premises should be and in the cloud should be bidirectional. No direct egress to the public internet except for control panel traffic. Resource groups managed by Azure Spring Apps deployment must not be modified. Subnets managed by Azure Spring Apps deployment must not be modified. Following list shows the component of that make up the design. On-premises network, DNS and gateway, hub subscription, application gateway subnet, Azure firewall subnet, shared services subnet, connection subscription, Azure Bastion subnet, and virtual network peer. The following list describes the Azure services in this reference architecture. Azure Key Vault, a hardware-backed credential management service that has tight integration with Microsoft Identity Services and compute resources. Azure Monitor, and all encompassing suite of monitoring services for applications that deploy both in Azure and on premises. Azure Pipelines, a fully features continuous integration, continuous deployment CI/CD service that can automatically deploy updated Spring Boot apps to Azure Spring Apps. Microsoft Defender Cloud, a unified security management that threat protection system for workloads across on premises, multiple clouds, and Azure Spring Apps, a managed service that's designed and optimized specifically for Java-based Spring Boot applications and .NET-based Steel Toy applications. Here you can see on-premises network is network interacts with virtual hub network through a resource route circuit. Gateway is inside on-premises network. Here here crop firewall is inside Azure firewall subnet, and crop application gateway is inside app gateway subnet. Express route gateway is inside gateway subnet. DNS services inside centralized services subnet. Azure firewall subnet, app gateway subnet, and centralized services subnet are inside hub virtual network. Hub virtual network is connected to Azure Spring Apps management addresses. Here hub virtual network is hub virtual network interacts with Spoke virtual network through virtual network peering. Spoke virtual network is connected to hub virtual network through through egress. On-premises network interacts with Spoke virtual network through ingress. Here hub virtual network is connected to DNS to virtual link, and Spoke virtual network is connected to DNS through a V-link. Here you can see Azure Spring Apps private DNS on. Service runtime subnet and app subnet and data services subnet are inside Spoke virtual network. App subnet is connected to data services subnet, and Azure Spring Apps are connected to service runtime subnet and app subnet. Azure load balancer, KPAC, config server and service registry are inside service runtime subnet. Azure load balancer and private FQDN inside apps subnet. Data services, Azure Cosmos DB and MongoDB are inside data services subnet. Spoke virtual subnet is connected to monitoring infrastructure, security infrastructure and CI/CD pipelines. Application insights, Azure Monitor are inside monitoring infrastructure. Key vaults, security center inside security infrastructure. Azure DevOps, Jenkins and GIT Hub, GitHub actions are inside CI/CD pipeline. CI/CD pipeline is connected to Spoke virtual network here in this way actually. Here you can see enterprise tier in private applications in Azure Spring Apps reference architecture. You can refer the standard tier for the description of other components here. Here you can see Azure load balancer, Tanzu build service, application configuration service, service registry, Spring Cloud Gateway and API portal are inside the service runtime subnet. Here you can see standard tier in public applications in Azure Spring Apps reference architecture. Here public application refers externally facing applications. With public applications, the following list describe the infrastructure requirements for public applications. These requirements are typically in highly regulated environments. A subnet must only have one instance of Spring Apps. Adherence to at least one security benchmark should be enforced. Application host domain name service records should be stored in private Azure private DNS. Azure DDoS protection should be enabled. Azure service dependencies should communicate through service endpoints or private link. Data at rest should be encrypted. Data in transit should be encrypted. DevOps deployment pipelines can be used, for example, Azure DevOps and require network connectivity to Azure Spring Apps. Egress traffic should travel through a central network virtual appliance NVA. For example, Azure Firewall. Ingress traffic should be managed by at least application gateway or this is the ingress traffic. Ingress traffic should travel through central network virtual appliance for NVA, for example, Azure Firewall here. Ingress traffic should be managed by at least application gateway or Azure front door. Internet routable addresses should be stored in Azure public DNS. Microsoft Zero Trust security approach requires secrets, certificates and credentials to be stored in a secure vault. The recommended service is Azure key vault. Name resolution hosts in on-premises and in the cloud should be bidirectional. No direct egress to public internet except for control panel traffic. Resource group managed by Azure Spring apps deployment must not be modified. Subnets managed by Azure Spring apps deployment must not be modified. The following list shows the components that make up the design: on-premises network, domain name service, DNS and gateway, hub subscription, application gateway subnet, Azure firewall subnet and shared services subnet, connection subscription, Azure Bastion subnet and virtual network peer. The following list describe the Azure services in reference architecture. Azure Azure Application Firewall, a feature Azure Application Gateway that provides centralized protection of applications from common exploits and vulnerabilities. Azure Application Gateway a load balancer responsible for application traffic with transport layer security TLS. Offload operating at layer 7. Azure Key Vault, a hardware-backed credential management service that has tight integration with Microsoft Identity Services and compute resources. Azure Monitor, all encompassing a suite of monitoring services for applications that deploy in both Azure and on-premises. Azure Pipelines, a fully featured continuous integration, continuous deployment, CI/CD service that can automatically deploy updated Spring Boot apps to Azure Spring apps. Microsoft Defender for Cloud, a unified security management that treats protection system for workload across on-premises, multiple clouds and Azure. Azure Spring Apps, a managed service that is designed and optimized specifically for Java-based Spring Boot applications and .NET-based Tiltoy applications. The following diagram represents well architectured hub and spoke design addresses above requirements. Only the hub virtual network communicates with the internet. Here you can see gateway is inside on-premises network. On-premises network interacts with hub virtual network through express route circuit. Here Azure Firewall subnet, Apps Gateway subnet and Centralized Services subnet are inside hub virtual network. Here ingress to App Gateway through ingress. Here Azure Firewall subnet from egress to internet through egress. Here crop firewall is inside Azure firewall subnet. Here crop application gateway is inside app gateway subnet. Here express route gateway is inside gateway subnet. Here DNS services are inside centralized services subnet. Spoke virtual network is connected to Azure firewall network here through egress, and Azure Firewall Network is connected to Spoke Virtual Network through Ingress. Here Hub Virtual Network is connected to Spoke Virtual Network through Virtual Network Peering, and Hub Virtual Network is connected to DNS through VNet link, and Spoke Virtual Network is connected to DNS through VNet link. Here you can see Azure Spring Apps Private DNS on. Service Runtime Subnet, App Subnet, and Azure Spring Apps and data services are inside Spoke Virtual Network. Azure Load Balancer, KPAC, Config Server, and Service Registry are inside Service Runtime Subnet. Private FQDN is inside App Subnet. Data services, Azure Cosmos DB, MongoDB are inside data services subnet. Spoke Virtual Network is connected to monitoring infrastructure and security infrastructure. CI/CD pipeline is connected to Spoke Virtual Network. Application Insights and Azure Monitor are inside monitoring infrastructure. Key Vault and Security Center are inside security infrastructure. Azure DevOps, Jenkins, and GitHub Actions are inside CI/CD pipelines. And CI/CD pipeline is connected to Spoke Virtual Network here. Here you can see enterprise tier in public applications in Azure Spring Apps Reference architecture. You can refer the standard tier in public applications in Azure Spring Architecture Reference, Spring Apps Reference Architecture for details of these components. Here you can see Azure Load Balancer, Tanzu Build Services, Service Application Configuration Service, Service Registry, Service Cloud Gateway, Spring Cloud Gateway, and API Portal inside Service Runtime Subnet. Here you can see CloudFoundry components. CloudFoundry components include self-service application execution engine and automatic engine for application deployment and lifecycle management, and scriptable command line interface CLI, as well as integration with development tools to easy deployment process. CloudFoundry has an open architecture that includes build-back mechanism for adding frameworks and application services, services interface, and cloud provider interface. Sorry, see the here routing. The router routes incoming traffic to the appropriate component. Either a cloud controller component or a hosted application running on Diago cell. On a Diago cell, a router periodically queries the Diago bulletin board system to determine which cells and containers each application currently runs on. Using this information, router can encompass new routing tables based on the IP addresses of each virtual shell, each cell virtual machine, and the host side port numbers for each cell's containers. Authentication, Auth2 server, UAA, and logging server. The OAuth2 server, the UAA and logging server work together to provide identity management, apps lifecycle, cloud controller, and Diago Brain. The cloud controller CC directs the deployment of applications. To push an app to CloudFoundry, you target the cloud controller. Cloud controller then directs the Diago Brain through CC bridge components to coordinate individual Diago cells to stage and run applications. Cloud controller also maintain records of orgs, spaces, user roles, services, and more. NSYNC, BBS, and cell reps. To keep application available, cloud deployment must constantly monitor their states and reconcile them with their expected states, starting and stopping processes as required. NSYNC's BBS and cell rep components work together along with the chain, along a chain to keep apps running. At one end is the user, at the other end are instances of application running on widely distributed VMs which may crash or become available. App storage and execution. Blob store. The blob store is a repository for large binary files which GitHub cannot easily manage because GitHub is designed for code. The blob store contains following: application code packages, build packs, and droplets. You can configure blob store as either an internal server or an external S3 or S3 compatible endpoint. Diago cell, application instances, application tasks, and staging tasks all run as garden containers on Diago cell VMs. Diago cell rep component manages lifecycle of those containers and the processes running in them reports their status to Diago BBS and emits their logs and matrices to Logata. Services, service brokers. Applications typically depends on services such as database or third-party SaaS providers. When a developer provisions and binds service to an application, the service broker for that application is responsible for providing the service instance. Messaging, internal HTTPS and BBS. CloudFoundry components VMs communicate with each other internally through HTTP or HTTPS protocols, sharing temporary messages and data stored in Diago's bulletin board system BBS. BOSH director collocates a BOSH DNS server on every deployed VM. All VMs keep up-to-date DNS records for all other VMs in the same foundation, enabling service discovery between VMs. BOSH DNS also provide the client-side load balancing by randomly selecting a healthy VM when multiple VMs are available. Diago bulletin board system BBS stores more frequently updated disposable data such as cell and app status, unallocated work and heartbeat messages, as well as longer lived distributed logs. The BBS stores data in MySQL using the Go MySQL driver. root emitter component uses NATS protocol to broadcast the list routing tables to the routers. Metrics and logging. Log aggregator or log aggregator system streams application logs to developers. Metrics collector. The metrics collector gathers metrics and statistics from the components. Operators can use this information to monitor CloudFoundry deployment. Here you can see router is in routing. Below that AOT 2 server, UAA and logging server is in authentication. Below that cloud controllers, NSYNC, Diago Brain and cell reps are in apps lifecycle. Blob store and apps execution, Diago cell are in app storage and execution. Garden is inside apps execution, Diago cell. Service brokers are inside services. BBS, HTTP and HTTPS console and NATS message bus are inside messaging. Metrics controller and app log aggregator are inside metrics and logging. Here you can see app lifecycle in CloudFoundry. NSYNC, BBS and cell reps. To keep applications available, cloud deployment must constantly monitor their states and reconcile them with their expected states, starting and stopping processes as required. The NSYNC, BBS and cell rep components work together along a chain to keep apps running. At one end is the user. At the other end are the instances of applications running on widely distributed VMs, which may crash or become unavailable. Here's how the components work together. NSYNC receives a message from cloud controller when the user scales an app. It writes the number of instances into a desired LRP structure in the Diago BBS database. BBS uses this convergence process to monitor the desired LRP and actual LRP values. It launches or stops application instances as appropriate to ensure actual LRP count matches the desired LRP count. Cell reps monitors the containers and provides the actual LRP value. Here you can see a user is connected to cloud controller. Cloud controller interacts with the CCDB and NSYNC is connected to cloud controller and desired LRP. Desired LRP and actual LRPs are connected to BBS. Converge is connected to desired LRP and actual LRPs, and cell rep is connected to actual LRPs and containers. Containers are connected to Garden. As an example, we are considering discovery in Spring Cloud for CloudFoundry. Here's a Spring Cloud apps with CloudFoundry discovery. This is app.groovy. If you run how's here, and the interface discovery client represent read operations commonly available on discovery service such as Netflix, Eureka, or console.io. This is in the package Ogre Spring Framework client.discovery. And if you run it without any service bindings, you can here you can see the commands. It will show its app name in the home page. The discovery client can list all apps in a space according to the credentials. It is authenticated with an where the space default to one of the clients is running in, if any. If neither org nor space are configured, they default per the user's profiles in CloudFoundry. Example 2, we are considering at enable OAuth 2 SSO. All of the OAuth 2 SSO and resource server features moved to Spring Boot in version 1.3. You can find the documentation in the Spring Boot user guide. This is regarding to single sign-on. This project provides automatic binding from CloudFoundry service credentials to the Spring Boot features. If you have CloudFoundry service called SSO, for instance, with credentials containing client ID, client secret, and auth domain, it will bind automatically to the Spring OAuth 2 client that you enable with at enable OAuth 2 SSO from Spring Boot. The name of the service can be parameterized using spring.oauth2.sso.service ID. Annotation type enable OAuth 2 SSO deprecated. Enable OAuth 2 single sign-on SSO if there is an existing web security configurer adapter provided by the user and annotated with at enable OAuth 2 SSO. It is enhanced by adding an authentication filter and an authentication entry point. If the user only has at enabled OAuth 2 SSO but not on web security configurer adapter, then one is added with all paths secured. This in the package org.spring framework.boot.autoconfigure.security.oauth2.client. Now we are focusing on API gateway. With so many clients and servers in play, it is often helpful to include an API gateway in your cloud architecture. A gateway can take care of securing and routing messages, hiding services, throttling load, and many other useful things. Spring Cloud Gateway gives you precise control of your API layer, integrating Spring Cloud Service Discovery and client-side load balancing solutions to simplify configuration and maintenance. Here you can see a high-level overview of how Spring Cloud Gateway works. Here the clients make request to Spring Cloud Gateway. If the gateway handler mapping determines that the request matches a route, it is sent to the gateway web handler. This handler runs a request through a filter chain that is specific to the request. The reason the filters are divided by the dotted line is that the filters can run logic both before and after the proxy request is sent. All pre-filter logic is executed, then the proxy request is made. After the proxy request is made, the post-filter logic is run. URIs define in routes without a port get default port values of 80 and 443 for HTTP and HTTPS URIs respectively. Here you can see a gateway client interacts with gateway handler mapping. Gateway handler mapping, gateway web handler, filters and proxy filters are inside the Spring Cloud Gateway. Gateway handler mapping interacts with gateway web handler. Gateway web handler interacts with filters. And here gateway web handler is connected to filter, and request is passed here. Then you can see proxy filter, then it is passed to the proxy service, then proxy service is connected to go through proxy filters, and it is connected to gateway web handler. Here you can see Spring Cloud gateway architecture. It consists of the following building blocks: root, the basic building blocks of the gateway. It consists of ID, destination URL, collection of predicates, and a collection of filters. Predicate. This is similar to Java 8 function predicate. Using this functionality, we can match HTTP requests such as headers, URL, cookies, or parameters. Filter. These are instances. Spring Framework. These are instances Spring Framework gateway filter. Using this, we can modify the request or response as per requirement. When a client makes a request to the SCG, the gateway handler mapping first check if the request matches a root. This matching is done using the predicates. If it matches the predicate, then the request is sent to the filters. Here clients interacts with the gateway handler mapping through request and response, and client is connected to gateway handler mapping through request, and gateway handler mapping is connected to predicate through request. Predicate is connected to pre-filter. Pre-filter is connected to services through requests. Services are connected to post filter through responses. Post filter is connected to gateway handler mapping. Gateway handler mapping is connected to client through response. Predicate, pre-filter, post filter, and gateway handler mapping are inside Spring Cloud Gateway. As an example, we can consider this code segment. To run your own gateway, use the Spring Cloud Starter Gateway dependency. As an example too, we are considering how to include Spring Cloud Gateway. Here you can see artifact ID Spring Cloud Starter Gateway, Spring Cloud Starter. To include Spring Cloud Gateway in your project, use the starter with the group ID org.springframework.cloud, and an artifact ID of Spring Cloud Starter Gateway. If you include the starter but you do not want the gateway to be enabled, set spring.cloud.gateway.enabled equal false. Spring Cloud Gateway is built on Spring Boot 2.x, Spring Web Flux, and Project Reactor. As a consequence, many of the familiar synchronous libraries, Spring Data and Spring Security for example, and patterns you know may not apply when you use Spring Cloud Gateway. If you are unfamiliar with these projects, we suggest you begin by reading their documentation to familiarize yourself with some of the new concept before working with Spring Cloud Gateway. Spring Cloud Gateway requires a netty runtime provided by Spring Boot and Spring Web Flux. It does not work in a traditional servlet container or when built as a WAR. As an example 3, we can consider interface gateway filter. Contract for interception style chained processing of web requests that may be used to implement cross-cutting application agnostic requirements such as security, timeouts, and others specific to a gateway copied from web filter. This is in the package org.springframework.cloud.gateway.filter. In example 4, we are considering shortcut configuration in configuring root predicate factories and gateway filter factories. Shortcut configuration is recognized by the filter name followed by an equal sign followed by an argument values separated by commas. This is the file application.yml. In this example defines a cookie root predicate factory with two arguments, the cookie name myCookie and the value to match myCookie value. Here you can see fully expanded arguments. Fully expanded arguments appear more like standard YAML configuration with name value pairs. Typically there will be a name key and an args key. The args key is a map of key value pairs to configure the predicate or filter. Here the application.yml. This is a full configuration of the shortcut configuration of the cookie predicate shown here. In example 5, we are considering after root predicate factory in root predicate factories. The following example configures an after root predicate. This is in application.yml. The after root predicate factory takes one parameter, a date time, which is Java sound date time. This predicate matches requests that happen after the specified date time. The following example configures an after route predicate. This route matches any request made after January 20, 2017, 1742 Mountain Time, Denver. As an example 6, we are considering modifying the way remote addresses are resolved. This example shows how to achieve the similar configuration in Java. This is we save this file as gateway config.java. The class xforward remote address resolver passes the client address from xforward for header. If header is not present, fall back to the remote address resolver. And serve http request dot get remote address method. Use the static constructor method which meets your security requirements. This is in the package org.springframework.cloud.gateway.support.ip resolver. By default, the remote ADDR root predicate factory uses the remote address from the incoming request. This may not match the actual client IP address if Spring Cloud Gateway sits behind a proxy layer. You can customize the way that the remote address is resolved by setting a custom remote address resolver. Spring Cloud comes with one non-default remote address resolver that is based off of the xforwarded for header, xforwarded remote address resolver. Xforwarded remote address resolver has two static constructor methods which take different approaches to security. Xforwarded remote address resolver trust all returns a remote address resolver that always takes the first IP address found in the xforwarded for header. This approach is vulnerable to spoofing, as a malicious client could set an initial value for the xforwarded for which would be accepted by the resolver. Xforwarded remote address resolver max trust index takes an index that correlates to the number of trusted infrastructure running in front of Spring Cloud Gateway. If the Spring Cloud Gateway is, for example, only accessible through HA proxy, then the value of 1 should be used. If two hops of trusted infrastructure are required before Spring Cloud Gateway is accessible, then the value of 2 should be used. Consider the following header value. The following max trusted index values yield the following remote addresses. max trusted index integer dot min value or 0. Result is invalid illegal argument exception during initialization. Value 1, result is 0.0.3. Value 2, result is 0.0.0.2. Index 3, result is 0.0.0.1. Index 4, integer dot max value 0.0.0.1. The following example shows how to achieve the same configuration with Java. As an example 7, we are considering the add request header gateway filter factory in gateway filter factories. The following example configured an add request header gateway filter. The method public gateway filter spec add request header string request header name and string request header value. Add the request header to the request before it is routed by gateway, and in Java it is in the interface gateway filter contract for interception style chain processing of web requests that may be used to implement cross-cutting application agnostic requirements such as security, timeout and others specific to gateway copied from web filter. If you use these methods and interfaces if you use Java configuration, and the interface gateway filter is in org.springframework.cloud.gateway.filter. The add request header gateway filter factory takes a name and value parameter. The following example configures an add request header gateway filter. This is application.yml file, and this listing adds x request red colon blue header to the downstream request headers of all matching requests. As an example 8, we are considering Spring Cloud Circuit Breaker Gateway Filter Factory. The following listing does the similar thing in Java. The Spring Cloud Circuit Breaker Gateway the Spring Cloud Circuit Breaker Gateway Filter Factory uses the Spring Cloud Circuit Breaker APIs to wrap gateway routes in a circuit breaker. Spring Cloud Circuit Breaker supports multiple libraries that can be used with Spring Cloud Gateway. Spring Cloud supports Resilience 4J out of the box. To enable the Spring Cloud Circuit Breaker filter, you need to place Spring Cloud Starter Circuit Breaker Reactor Resilience 4J on the class path. The following example configures Spring Cloud Circuit Breaker Gateway filter to configure the circuit breaker, see the configuration for the underlying circuit breaker implementation you are using. The Spring Cloud circuit breaker filter can also accept an optional fallback URI parameter. Currently only forward schemed URIs are supported. If the fallback is called, request is forwarded to the controller matched by the URI. This example configures such a fallback. Following listing does the same thing in Java. In this example forwards to the / in case of failure, use this URI when the circuit breaker fallback is called. Note that this example also demonstrates the optional Spring Cloud load balancer load balancing defined by the LB prefix on the destination URI. Circuit breaker also supports URI variables in the fallback URI. This allows more complex routing options like forwarding sections of the original host or URL path using path pattern expression. As an example 9, we are considering combined global filter and gateway filter ordering in global filters. Following listing configures filter chain. The interface global filter contract for interception style chain processing of web requests that may be used to implement cross-cutting application agnostic requirements such as security, timeouts, and others. The interface gateway filter chain contract to allow a web filter to delegate to the next in the chain. This design the package org.springframework.cloud.gateway.filter. When a request matches a route, the filtering web handler adds all instances of global filter and all route specific instances of gateway filter to a filter chain. This combined filter chain is shorted by the org.springframework.core.ordered interface, which you can set by implementing the get order method. As Spring Cloud Gateway distinguishes between pre and post phases for filter logic execution, the filter with the highest precedence is the first in the pre phase and the last in the post phase. The following listing configures a filter chain. As an example 10, we are considering the reactive load balancer client filter. The following listing configures a reactive load balancer client filter. This is in application.yml. The class reactive load balancer client filter, a global filter implementation that routes requests using reactive Spring Cloud Load Balancer. This is in the package org.springframework.cloud.gateway.filter. The reactive load balancer client filter looks for a URI in the exchange attribute named server web exchange util.gateway request URL attr. If the URL has the LB scheme, such as LB colon my service, it uses the Spring Cloud Reactor Load Balancer to resolve the name my service, for example, to an actual host and port, then replaces the URL in the same attribute. The unmodified original URL is appended to the list in the server web exchange utils.gateway original request URL attr attributes. The filter also looks for the server web exchange utils.gateway scheme prefix attr attributes to see if it equals LB. If so, the same rules apply. The following listing configures reactive load balancer client filter here. By default, when a service instance cannot be found by the reactor load balancer, 503 is 503 is returned. You can configure the gateway to return 404 by setting spring.cloud.gateway.loadbalancer.use 400 404 equal true. The is-secure value of service instance returned from the reactive load balancer client filter overrides the scheme specified in the request made to the gateway. For example, if the request comes into the gateway over HTTPS but the service instance indicate it is not secure, the downstream request is made over HTTP. The opposite situation can also apply. However, if gateway scheme prefix attr is specified for the root in the gateway configuration, the prefix is stripped and resulting scheme from the root URL overwrite the service instance configuration. Gateway supports all the load balancer features. As an example 11, we are focusing on X-forwarded headers filter in HTTP headers filters. Creating an individual headers can be controlled by the following Boolean properties: default to true. In the API, this interface HTTP headers filter that is in the package org.springframework.cloud.gateway.filter.headers. The X-forwarded headers filter creates a creates various x dash forwarded dash asterisk headers to send the downstream service. It uses the host header scheme, port, and path of the current request to create the various headers. Creating an individual headers can be controlled by the following Boolean properties: default to true. Yeah. Now we are considering TLS and SSL. The gateway can listen for requests on HTTPS by following the usual Spring Server configuration. The following example shows how to do so. You can route gateway routes to both HTTP and HTTPS backends. If you are routing to an HTTPS backend, you can configure the gateway to trust all downstream certificates with the following configuration. Now we are considering configuration. Here we are considering the interface route definition locator, which is in the package org.springframework.cloud.gateway.root. Configuration for Spring Cloud Gateway is driven by a collection of route definition locator instances. By default, a properties route definition locator loads properties by using the Spring Boot's at configuration properties mechanism. This example, early examples all use the shortcut notation that uses positional argument rather than named one. Following two examples are equivalent. For some usages of the gateway, properties are adequate, but some production use cases benefit from loading configuration from an external source such as a database. Future milestone versions will have route definition locator implementations based off of Spring data repositories such as Redis, MongoDB, and Cassandra. Now we are considering route metadata configuration. You can configure additional parameters for each route by using metadata as follows. The method public map string object get metadata. This is in the class route in package org.springframework.cloud.gateway.root. You could acquire all metadata properties from Exchange as follows. Here get all metadata properties. Here get a single metadata property. Now we are considering HTTP timeouts configuration. Global timeouts. In global timeouts, Here the global timeouts example. To configure global HTTP timeouts, connect timeout must be specified in milliseconds. Response timeout must be specified as a java.time.duration. Now we are considering per root timeouts. Per root timeouts configuration using Java DSL. To configure per root timeouts, connect timeout must be specified in milliseconds, and response timeout must be specified in milliseconds. Here per root HTTP timeouts configuration via configuration. As per timeout as per root response timeout with negative value will disable the global response timeout value. Now we are considering reactor netty access logs. The following example creates a logback configuration. To enable reactor netty access logs, set dash d reactor.netty.http.server.access log enabled equal true. You can configure logging system to have a separate access log file. The following example creates a logback configuration. Now we are considering CORS configuration. The following example configures CORS. This is in application.yml. The global CORS configuration is a map of URL patterns to Spring Framework CORS configuration. Following example configures CORS. In this example, CORS requests are allowed from requests that originate from docs.spring.io for all get requested paths. To provide some CORS configuration to requests that are not handled by some gateway root predicate, set the spring.cloud.gateway.global CORS.add to simple URI handler mapping property to true. This is useful when you try to support CORS pre-flight requests and your root predicate does not evaluate to true because the HTTP method is options. Now we are considering Actuate API. The following listing shows how to do it, and the /gateway actuator endpoints let you monitor and interact with the Spring Cloud Gateway application. To be remotely accessible, the endpoint has to be enabled and exposed over HTTP or JMX. In the application properties, the following listing shows how to do so. Default value. Now we are considering verbose actuator format. The following example configured actuator gateway routes. A new, more verbose format has been added to Spring Cloud Gateway. It adds more details to each route, letting you view predicates and filters associated with each route, along with the any configuration that is available. The following example configured /actuator /gateway /routes. This feature is enabled by default. To disable, set the following property: spring.cloud.gateway.actuator.verbose.enabled equal false. This is in application.properties. This will default to true in future release. Now we are considering retrieving root values. We are considering global filters in retrieving root filters. The resulting response is similar to the following. To retrieve global filters, apply to all routes, make a GET request to /actuator /gateway /global filters. The resulting response is similar to the following. Each response contains the details of the global filters that are in place. For each global filter, there is a string representation of the filter object. For example, org.springframework.cloud.gateway.filter.reactive load balancer client filter at 77856 CC5 and the corresponding order in the filter chain. Root filters. To retrieve the gateway filter factories, apply to routes, make a GET request to /actuator /gateway /root filters. The resulting response is similar to the following. The response contains the details of the gateway filter factories applied to any particular route. For each factory, there is a string representation of the corresponding object. For example, for example, secure headers gateway filter factory at FCE AB5D config class equal object. Note that the null value is due to an incomplete implementation of the endpoint controller, because it tries to set the order of the object in the filter chain, which does not apply to a gateway filter factory object. Now we are considering the log levels in troubleshooting. The following loggers may contain valuable troubleshooting information at the debug and trace levels. Now we are considering writing custom root predicate writing custom root predicate factories. There's an abstract class called abstract root predicate factory, which you can extend. The class abstract root predicate factory, C, this is in the package org.spring framework.cloud.gateway.handler.predicate. In order to write a root predicate, you will need to implement root predicate factory as a bean. There is an abstract class called abstract root predicate factory, which you can extend. Grab configuration from config object. Grab the request. Take information from the request to see if it matches the configuration. Put the configuration properties for your filters here. Now we are focusing on writing custom gateway filter factories. The following example shows how to do so. The class abstract gateway filter factory C. This is in the package org.spring framework.cloud.gateway.filter.factory. To write a gateway filter, you must implement gateway filter factory as a bean. You can extend an abstract class called abstract gateway filter factory. Following example shows how to do so. And here you can see a post gateway filter factory. Grab configuration from config object. If you want to build a pre-filter, you need to manipulate request before calling chain.filter. Use builder to manipulate the request. Put the configuration properties for your filter here. Grab configuration from config object, and here the manipulate the response in some way, and here put the configuration properties for your filter here. Now we are considering writing custom global filters. The following example shows how to set up global filter pre and post filters respectively. The interface global filter contract for interception style chain processing of web requests that may be used to implement cross-cutting application agnostic requirements such as security, timeouts, and others. This is in the package Spring framework.cloud.gateway.filter. To write a custom global filter, you must implement global filter interface as a bean. This applies the filter to all requests. The following example shows how to get set up global pre and post filters respectively. Adds headers to proxies request. Adds headers to the response. Now we are considering building a simple gateway by using MVC or Webflux. The following MVC example proxies request to /test downstream to a remote server. The following describes an alternate server, and the class proxy exchange T at request mapping argument type that can proxy the request to a backend. Spring will inject one of these into a MVC handler method, and you can get return a response entity that you get from one of the HTTP methods get, post, put, patch, delete, etc. And for an example, you can see at get mapping here. By default, the incoming request body and and the headers are sent intact to the downstream service with exception of sensitive headers. To manipulate the downstream request via a builder style methods in proxy exchange, but only the URI string is mandatory. You can change sensitive headers by calling the sensitive string method. Authorization and cookie are sensitive by default. The following describes an alternative style gateway. None of the prior documentation applied to what follows. The Spring Cloud Gateway provides a utility object called proxy exchange. You can use it inside a regular Spring Web Handler as a method parameter. It supports the basic downstream HTTP exchanges through methods that mirror HTTP verbs. With MVC, it also supports forwarding to a local handler through the forward method. To use the proxy exchange, include the right module in your class path, either Spring Cloud Gateway MVC or Spring Cloud Gateway Webflux. The following MVC example proxies a request to /test downstream to a remote server. Following example does the same thing with Webflux. Now we are focusing on configuration properties. We are considering spring.cloud.gateway.default filters here. Various properties can be specified inside the application.properties file, inside the application.yml file, or as command line switches. So here the property spring.cloud.gateway.default filters. As an exception example, we are considering a class not found exception. This is in the package org.springframework.cloud.gateway.support. As an example, we can consider this one, fail to resolve desktop etc. after 4 queries, etc. And here you can see error has been observed at the following sites: checkpoint, org.springframework.cloud.gateway.filter.wait, calculator, web filter, etc. Now we are focusing on Spring Boot apps. As an example, we are considering here this CLOUDFOUNDRY. The following line shows using the cf push command to deploy an application. CLOUDFOUNDRY provides default build pack that come into play if no other build pack is specified. The CLOUDFOUNDRY Java build pack has excellent support for Spring applications, including Spring Boot. You can deploy standalone executable Java applications as well as traditional .var package applications. Once you have built your application using, for example, mvn clean package, and have installed the cf command line tool, deploy your application by using the cf push command, substituting the path to your compiled jar. Be sure to have logged in with your cf command line client before pushing an application. The following line shows using cf push command to deploy an application. In the preceding example, we substitute a cloudy springtime for whatever value you give cf as the name of your application. If there is a CLOUDFOUNDRY manifest.yml file present in the same directory, it is considered. At this point, cf start uploading your application, producing output similar to the following example. Configuration congratulations, the application is live now. Once your application is live, you can verify the status of the deployed application by using the cf apps command as shown in this in the following example. Once CLOUDFOUNDRY acknowledge that your application has been deployed, you should be able to find the application at the URI given. In this example, you can find it at cloudyspringtime.cf http:// cloudyspringtime.cfapps.io/. By default, now we are considering a binding to services. By default, metadata about running an application as well as service connection information is exposed to the application as environment variables. For example, $vcap_services. This architecture design is due to CLOUDFOUNDRY's polyglot. Any language and platform can be supported as a build pack nature. Process scoped environment variables are language agnostic. Environment variables do not always make for the easiest API, so Spring Boot automatically extract them and flatten the data into properties that can be accessed through Spring's environments abstraction, as shown in the following example. All CLOUDFOUNDRY properties are prefixed with vcap. You can use vcap properties to access application information, such as the public URL of an application and service information such as database credentials. The Spring Cloud Connectors project is a better fit for tasks such as configuring a data source. Spring Boot includes auto configuration support and Spring Boot Starter Cloud Connectors Starter. Now we are considering Kubernetes. The pre-stop handler can be configured by using the pod spec in the pods configuration file as follows. With Kubernetes container lifecycle, when Kubernetes deletes an application instance, the shutdown process involves several subsystems concurrently. Shutdown hooks, unregistering the service, removing the instances from the load balancer because the shutdown process happens in parallel, and due to the nature of distributed systems, there's a window during which traffic can be routed to a pod that has also begun in its shutdown processing. You can configure a sleep execution in the pre-stop handler to avoid request being routed to a pod that has already begun shutting down. This sleep should be long enough for new request to stop being routed to the pod, and its duration will vary from deployment to deployment. The pre-stop handler can be configured by using the pod spec in the pods configuration file as follows. Once the pre-stop hook has completed, SIGTERM will be sent to the container and graceful shutdown will begin, allowing any remaining in-flight requests to complete. When Kubernetes sends SIGTERM signal to the pod, it's wait for a specified time called the termination grace period, the default for which is 30 seconds. If the containers are still running after a grace period, they are sent to kill signal and forcibly removed. If the pod takes longer than 30 seconds to shut down, which could be because you have increased spring.lifecycle.time out per shutdown pace, make sure to increase the termination grace period by setting termination grace period seconds option in the pod YAML. Now we are considering Heroku. The most common deployment workflow for Heroku deployment is the git push the code to the production, as shown in the following example here. Heroku is another popular PaaS platform. To customize Heroku builds, you provide proc file which provides the incantation required to deploy an application. Heroku assigns a port for the Java application to use, and then ensures that routing to an external URI works. You must configure your application to listen on the correct port. The following example shows the proc file for our starter REST application here. The Spring Boot makes -d arguments available as properties accessible from a Spring environment instance. The server.port configuration property is fed to the embedded Tomcat, Jetty, or Undertow instance, which then uses the port when it starts up. $port environment variable is assigned to us by the Heroku PaaS. This should be everything you need. Most common deployment workflow for Heroku deployment is to git push the code to production, as shown in the following example, which will result in the following. Yeah. Your application should now be up and running on Heroku. Now we are considering using OpenShift for enterprise grade application boot deployment. To have the Spring Boot builder working on your OpenShift 3 installation, follow these simple steps here. Now we are considering using the Java SC platform in AWS Elastic Beanstalk. Elastic Beanstalk environments run an Nginx instance on port 880 to proxy the actual application running on port 5000. To configure it, add the following line to your application .properties file. This option applies to Spring Boot projects that produce a jar file and run an embedded web container. By default, Elastic Beanstalk uploads sources and compiles them in AWS. However, it is best to upload the binaries instead. To do so, add lines similar to the following your .elasticbeanstalk/config.yml file. By default, an Elastic Beanstalk environment is load balanced. The load balancer has a significant cost. To avoid that cost, set the environment type to a single instance. You can also create single instance environments by using the CLI and the following command. Now we are considering Cloud Captain and Amazon Web Services. Once you have created the Cloud Captain account, the connected to it to your AWS account, install the latest version of Cloud Captain client and ensure that the application has been built by Maven or Gradle by using, for example, MEN clean package. You can deploy your Spring Boot application to AWS with a command similar to the following here. Cloud Captain works by turning your Spring Boot executable jar or var into a minimal VM image that can be deployed unchanged either on VirtualBox or on AWS. Cloud Captain comes with the deep integration for Spring Boot and uses the information from your Spring Boot configuration file to automatically configure the ports and health check URLs. Cloud Captain leverages this information both for the images it produces as well as all the resources it provisions, instances, security groups, Elastic load balancers, and so on. Once you have created the Cloud Captain account, connected it to your AWS account, install the latest version of the Cloud Captain client and ensure that the application has been built by Maven or Gradle by using, for example, MEN clean package. You can deploy your Spring Boot application to AWS with the command similar to the following. If there is a boxfuse.config file present in the current directory, it is considered. By default, the Cloud Captain activates the Spring profile named boxfuse on startup. If your executable jar or var contains an application-boxfuse.properties file, Cloud Captain bases its configuration on the properties it contains. At this point, Cloud Captain creates an image for your application, upload it and configure it, and it starts necessary resources on AWS, resulting the output similar to the following example here. Your application should now be up and running on AWS. Now we are considering deploying deploying a Spring Boot app to Azure. Config and deploy the app to Azure Spring Apps. Step 1, before started, you will need to provision an Azure Spring Apps cluster, for instance using Azure Portal. Step 2, from the terminal window, configure your web app with Maven plugin for Azure Spring Apps by typing ./menw com.microsoft.azure Azure Spring Cloud Maven plugin 1.3.0 config. This Maven goal will first authenticate with Azure. If you have logged in with Azure CLI, it will consume its existing authentication token. Otherwise, it will get you logged in with Azure Maven plugin automatically. Step 3, then you can configure the deployment. Run the Maven command in the command prompt. And select Azure Spring select Azure Spring cluster you just created. Accept default app name and then press yes to expose public access for this app. When you get the confirm yes no prompt, press press Y and the configuration is done. Optionally, open your pom.xml to see all the configuration written. Once you have configured step 5, once you have configured all the settings in the preceding sections, you are ready to deploy your web app to Azure Spring Apps with MUN Azure-Spring-Cloud deploy. Maven will deploy your web app to Azure. It might take a few minutes before the web app is accessible at the URL shown in the output. Navigate to the URL in a web browser. You should see the message displayed, greeting from Spring Boot. Note that the simple Spring Boot app is not using the Spring Cloud component like Discovery Client. Thus, registration status will down while the app is up and running. So this so code for the app is not given here, just the deployment process. Now we are considering Google Cloud. Normally you put this file in src/main/app engine and it should resemble the following file. Google Cloud has several options that can be used to launch Spring Boot applications. The easiest to get started with is probably App Engine. You could also find ways to run Spring Boot in a container with Container Engine or on a virtual machine with Compute Engine. To run in App Engine, you can create a project in the UI first, which set up a unique identifier for you and also set up HTTP routes. Add the Java app to the project and leave it empty, and then use Google Cloud SDK to push your Spring Boot app into that slot from command line or CI build. App Engine standard requires you to use WA packaging. Alternatively, App Engine Flex requires you to create an app.yml file to describe the resources your application requires. Normally, you put this file in source src/main/app engine, and it should resemble the following file here. You can deploy the app, for example, with the Maven plugin by adding the project ID to the build configuration as shown in the following example here. Then deploy with mvn app engine :deploy. If you need to authenticate first, the build fails. Now we are focusing on metrics store, generally a time series database. Here you can see the general architecture of how streaming applications are monitored. String monitoring with Prometheus, Wavefront, and InfluxDB. This section describes how to monitor the application that were deployed as part of stream data pipeline. The setup for each platform is different, but the general architecture is the same across all the platforms. The data flow metrics architecture is designed around the micrometer library to provide the simple facade over the instrumentation clients for the most popular monitoring systems. Micrometer powers the delivery of application metrics from Spring Boot. Spring integration provide additional micrometer integration to expose metrics around to expose metrics around message rates and errors, which are critical to the monitoring and of deployed streams. All Spring Cloud Stream app starters and string applications are pre-configured to support 3 of the most popular monitoring systems: Prometheus, Wavefront, and InfluxDB. You can declaratively select which monitoring system the deployed applications used. To help you get started monitoring systems, Dataflow provides Grafana dashboards for Prometheus and Influx that you can install and customize for your needs. For Wavefront, you can use the Dataflow integration tile for rich and comprehensive metrics visualization. The following image shows the general architecture of how streaming applications are monitored. Here you can see here you can see data flow server interacts with the skipper server, and you can see the micrometer here, and micrometer is connected to time series database through metrics, and skipper server is connected to streams is connected to here, stream lifecycle management, and here the source processor and sync are inside streams, local, Kubernetes, and CloudFoundry. Source is connected to processor and processor is connected to sync, and micrometers are connected to time series database through metrics. Here you can see time series database, Prometheus, Wavefront, InfluxDB, etc. Time series database is connected to dashboards. Here skipper server is connected to streams. Additionally, for streaming data pipelines based on Kafka binder or dedicated Kafka and Kafka stream dashboard is provided based on the Apache Kafka metrics. Prometheus requires a service discovery component to automatically probe the configured endpoints for metrics. The Spring Cloud Dataflow server uses Prometheus RSocket proxy, which uses RSocket protocol for the service discovery mechanism. The RSocket proxy approach is used so that we can monitor tasks which are short-lived as well as long-lived stream applications by using the same architecture. In addition, the RSocket approach lets the same monitoring architecture be used across all platforms. Prometheus is configured to scrape each proxy instances. Proxies in turn use RSocket connection to pull metrics from each application. The scrapped metrics are then viewable through Grafana dashboards. Here you can see the brokers are inside Apache Kafka. Source is connected to producer and micrometer, and producer is connected to broker here. Broker is connected to consumer through messages, and the process is connected to consumer and producer, and micrometers are here. And here the producer is connected to broker, and broker is connected to consume through messages. Here the sync is connected to consumer, and you can see the micrometer here, and micrometers are connected to time series database through metrics. Here you can see the general architecture of how task applications are monitored. Here we are considering task and batch monitoring with Prometheus and InfluxDB. This section describes how to monitor the applications that are deployed as part of a task definition in Dataflow. The setup for each platform is different, but the general architecture is same across platforms. The Dataflow metrics the Dataflow metrics architecture is designed around micrometer library, which is a vendor neutral application metrics facade. It provides simple facade over the instrumentation clients for most popular monitoring systems. Micrometer is the instrumentation library that powers the delivery of application metrics from the Spring Boot. Spring Batch provides additional integration to expose metrics around task durations, rates, and errors which are critical to the monitoring of deployed batch jobs. We focus on using 3 time series databases, Wavefront, Prometheus, and InfluxDB. Wavefront is a high performance streaming analytics platform that supports 3D observability, metrics, histograms, and traces and spans. It scales to very high data injection rates and query loads while also collecting data from many services and sources across your entire application task. Prometheus is a popular pool-based time series database that pulls the metrics from the targeted application with pre-configured endpoints and provides a query language to select and aggregate time series data in real time. InfluxDB is a popular open source push-based time series database. It supports downsampling, automatically expiring and deleting unwanted data, and backup and restore. Analysis of data is done through an SQL-like query language. The core of Micrometer task integration is a part of Spring Cloud Task 2.2.0 release line, which is a prerequisite for the task metrics and the data flow integration. You can configure task applications built on the Spring Task 2.2 plus version to emit task and batch metrics to the pre-configured monitoring system supported by Micrometer. Prometheus requires a service discovery component to automatically probe the configured endpoints for metrics. The Spring Cloud Dataflow Server uses Prometheus RRocket proxy, which uses RRocket protocol for the service discovery mechanism. The RRocket's proxy approach is used so that we can monitor tasks which are short-lived and long-lived stream applications by using the same architecture. In addition, the RRocket approach lets the same monitoring architecture to be used across all platforms. Prometheus is configured to scrap each proxy instance. Proxies in turn use RRocket connection to pull metrics from each application. The scrap metrics are then viewable through Grafana dashboard. Here you can see a task, local Kubernetes, CloudFoundry. Tasks are connected to task interacts with Dataflow server through task lifecycle management. Dataflow server is connected to Micrometer. Micrometer is connected to time series database through metrics, and tasks are connected to Micrometers. Micrometers are connected to time series database through metrics. Time series database, Prometheus, Wavefront, InfluxDB, etc. Is connected to dashboards. It interacts with dashboards. Here you can see. As an example, we are considering here the package org.springframework.boot.actuate.metrics. Core actuator supports for metrics. Now we are considering Prometheus in local in server monitoring with Prometheus and Wavefront. To install Prometheus and Grafana, follow the monitoring with Prometheus and Grafana Docker compose instructions. Doing so brings up the Spring Cloud Dataflow, Skipper, Apache Kafka, Prometheus, and pre-built dashboard for Grafana. Once all the containers are running, you can access the Spring Cloud Dataflow dashboard at http://localhost:9393/dashboard. You can also reach the Prometheus UI at http://localhost:9090/graph and http://localhost:9090/targets. You can access Grafana dashboard at http://localhost:3000 with the following credentials: user admin, password admin. You can access the server's dashboard at the following URL: http://localhost:3000/d/servers/servers ? Refresh equal 10s. The data flow matrix architecture is designed around the micrometer library to provide a simple facade over the instruction clients for the most popular monitoring systems. Data flow and skipper servers are pre-configured to support two of the most popular monitoring systems, Prometheus and Wavefront. You can declaratively select which monitoring system depend on the system the deployed application uses. To help you get started with monitoring systems, Dataflow provide Grafana dashboard for Prometheus that you can install and customize for your needs. Following image shows the Grafana. Now we are focusing on Wavefront. To install Dataflow with Wavefront support, follow the monitoring with Wavefront Docker Compose instructions. Doing so brings up the Spring Cloud Dataflow, Skipper, and Apache Kafka. It also points to the Wavefront Dataflow integration tile automatically. Wavefront is a SaaS offering, and you need to create a user account first. With that account, you can set the Wavefront key and Wavefront URI environment variables. The following image shows the Wavefront dashboard. Now we are considering Prometheus in Kubernetes. To install Prometheus and Grafana on Kubernetes, follow the instruction for a kubectl based installation. The address used to access the Grafana UI depends on the Kubernetes platform to which the system is deployed. If you are using, for example, GKE, the load balancer address is used. If you use Minikube, which does not provide the load balance implementation, the IP of the Minikube along with an assigned port is used. In the following examples, for simplicity, we use Minikube. To obtain the URL of the Grafana UI when it is deployed to Minikube, run the following command: Minikube service --URL Grafana http ://192.168.99.100:31595. You can access the Grafana dashboard at http://192.168.99.100:31595 with the following credentials: username admin, password. You can access the server's dashboard at http://192.168.99.100:scdf-servers/servers ? Refresh equal 10s. Now we are focusing on Wavefront. Wavefront is a SaaS offering. You need to create a user account first and obtain API key and Wavefront URI. assigned to your account. Follow the general data flow Kubernetes installation instructions. Then add the following properties to your Spring Cloud data flow server configuration. For example, in src /kubernetes /server dash config.yaml to enable Wavefront integration. To enable Spring Skipper Wavefront monitoring, replicate the same metrics configuration to the Skipper server configuration. For example, in src /kubernetes /skipper dash config dash kafka.yml or src /kubernetes /skipper config rabbit.yml. Now we are considering Prometheus in CloudFoundry. To configure the data flow servers manifest to send metrics data from stream application to the Prometheus RSocket gateway, follow the manifest dash based installation instructions. With Prometheus, Grafana, Spring Cloud data flow and any other services defined in the getting started CloudFoundry section up and running, you are ready to collect you are ready to collect metrics. This getting started CloudFoundry is in the documentation section. Depending on where you have installed Grafana, you can access the Grafana dashboard with the following credentials: username, admin, password. You can access the service dashboard at the following URL: http:///3000/d/scdf /servers refresh equal 10s. Now we are considering Wavefront in CloudFoundry. Wavefront is a SaaS offering. You need to create a user account first and obtain the app dash key and the Wavefront dash URI assigned to your account. To configure app data flow server to send metrics from stream application to Wavefront monitoring, follow the manifest based Wavefront configuration instructions in the documentation. Now we are considering Prometheus in local in stream monitoring with Prometheus, Wavefront and InfluxDB. To install Prometheus and Grafana, follow the monitoring with Prometheus and Grafana in documentation, Docker Compose instructions. Doing so brings up the Spring Cloud data flow, Skipper, Apache, Kafka, Prometheus, and pre-built dashboards for Grafana. Once all the containers are running, you can access the Spring Cloud data flow dashboard at http://localhost:9393/dashboard. Also, you can reach the Prometheus UI at http://localhost:9090 graph and http://localhost:9090 targets. You can access the Grafana dashboard at http://localhost:3000 by using the following credentials: user admin, password admin. There are two provisions dashboard. Streams http://localhost:3000/d/scdf-streams /streams refresh equal 10s. Applications http://localhost:3000/d/scdf-applications /applications refresh equal 10s. To see the dashboard in action, deploy a simple stream that uses Kafka. So you can see the lines here. So these two lines, this one and this one, should be in a single line. You should see the dashboard similar to those shown in the following image here. Now we are considering Wavefront. To install Dataflow with Wavefront support, follow the monitoring and with Wavefront Docker Compose instructions. Doing so brings up the Spring Cloud Dataflow skipper and Apache Kafka. It also points to Wavefront's Dataflow integration tile automatically. The Wavefront is a SaaS offering, and you need to create a user account first. With that account, you can set the Wavefront underscore key and Wavefront underscore URI environment variables as variables. You should see dashboard similar to those shown in the following image here. Now we are considering InfluxDB. To install InfluxDB and Grafana, follow the monitoring with Influx and Grafana Docker Compose instructions. Doing so brings up the Spring Cloud Dataflow skipper, Apache Kafka, Influx, and pre-built dashboards for Grafana. Once all the containers are running, you can access the Spring Cloud Dataflow dashboard at http ://localhost 9393/dashboard. You can access the Grafana dashboard at http ://localhost 3000 by using the following credentials. User admin, password admin. There are two provision dashboards streams, http ://localhost 3000/d scdf-streams :streams ? refresh = 10s. Applications, http ://localhost 3000/d scdf-applications :applications ? refresh = 10s. Now you can deploy a simple stream that uses Kafka, such as following. Here, this is one line, and these two lines should be in one line, single line. You should see the dashboard similar to those shown in the following example here. To validate the setup, you can log into those containers by using the following command here. Then you can check the content of InfluxDB by using following commands. Now we are considering Prometheus in Kubernetes. To install Prometheus and Grafana on Kubernetes, you need to follow the instructions for kubectl based installation. To obtain the URL of Grafana UI when it is deployed to Minikube, run the following command. You can access Grafana dashboard at http://192.168.99.100:31595 by using following credentials: username, admin, password. There are two provision dashboards: streams, http://192.168.99.100:31595 d/scdf dash streams /streams ? Equal 10s, and applications http://192.168.99.100:31595 d/scdf applications /applications ? Equal 10s. You can collect metrics on a per application, per stream basis, so apply metrics collection to all deployed applications globally. To deploy the single stream with metrics enabled, enter the following into the Spring Cloud data flow shell here. This should be in a single line. You should see the dashboards similar to those shown in the following example here. Now we are considering Wavefront in Kubernetes. Wavefront is a SaaS offering. You need to create a user account first and obtain the API-key and Wavefront-URI assigned to your account. Follow the general data flow Kubernetes installation instructions. Then add the following properties to your Spring Cloud data flow server configuration. For example, src kubernetes server config.yaml to enable Wavefront configuration. Then the Wavefront portal, you should see the dashboard similar to those shown in the following image here. Now we are considering Prometheus in CloudFoundry. To configure the data flow servers manifest to send metrics data from stream applications to Prometheus RSocket gateway, follow the manifest based installation instructions. With Prometheus, Grafana, Spring Cloud data flow, and any other services as defined in the getting started CloudFoundry section in the documentation up and running, you are ready to collect matrices. Depending on where you have installed Grafana, access the Grafana dashboard by using the following credentials: username, admin, password. There are two dashboards that can be installed by using following links: streams, this is the link, and applications, this is the link. And then you can collect matrices on per application, per stream basis, or globally apply matrices collection to all deployed applications. To deploy a single stream with metrics enables, enter the following into the Spring Cloud data flow shell. This must be in a single line. After deploying a stream, you can launch to view the Grafana dashboards as shown in the following image here. Now we are considering Wavefront in CloudFoundry. Wavefront is a SaaS offering. You need to create a user account first and then obtain the API-key and Wavefront-URI assigned to your account. To configure the data flow server to send metrics data from stream application to Wavefront monitoring system, follow the manifest-based Wavefront configuration instructions. Then on the Wavefront portal, you should see dashboard similar to those shown in the following image here. Now we are considering Prometheus in local in task and batch monitoring with Prometheus and InfluxDB. To install Prometheus and Grafana, follow the monitoring with Prometheus and Grafana Docker Compose instructions. Doing so brings up the Spring Cloud data flow, Skipper, Apache, Kafka, Prometheus, and pre-built dashboard for Grafana. Once all the containers are running, you can access the Spring Cloud data flow dashboard this address. You can reach the Prometheus UI at this address, and you can access the Grafana dashboard at this address, and by using the following credentials: user admin, password admin. Now you can deploy custom task application, task demo metrics, and define 2 tasks, task 1 and sorry, now you can deploy custom task application, task demo metrics, and define 2 tasks, task 1 and task 2. You can launch the task several times. In the data flow task execution UI, you should see the following: this one and another one here. Also in Grafana dashboard for tasks, you should see the following: now we are considering Wavefront. To install Dataflow with Wavefront support, follow the monitoring with Wavefront Docker Compose instructions. Doing so brings up Spring Cloud Dataflow, Skipper, and Apache Kafka. It also points to the Wavefront's Dataflow integration tile automatically. Wavefront is a SaaS offering. You need to create a user account first and use it to set the Wavefront _key and Wavefront _URI environment variables. You should see the dashboard similar to those shown in the following image here. Now we are considering InfluxDB. To install InfluxDB and Grafana, follow the monitoring with InfluxDB and Grafana Docker Compose instructions. Doing so brings up the Spring Cloud Dataflow, Skipper, Apache Kafka, InfluxDB, and pre-built dashboards for Grafana. Once all the containers are running, you can access the Spring Cloud Dataflow dashboard. That's from this address. You can access the Grafana dashboard at this address, http://localhost:2000 by using the following credentials: user admin, password admin. Now you can deploy custom task applications, task applications, task demo metrics, and define 2 tasks, task 1 and task 2. This should be in a single line. Then you can launch the task in several times. In Dataflow task execution, you should see a list like this. You should see dashboard similar to those shown in the following image. Now we are considering Prometheus in Kubernetes. To install Prometheus and Grafana on Kubernetes, you need to follow the instruction for kubectl-based installation. To obtain the URL of the Grafana UI when it is deployed to Minikube, run the following command here. And in the procedure example, you can reach the Grafana dashboard from this address. The default credentials are as follows: username admin, password. The Grafana instance is pre-provisioned with a dashboard. Task, and this is the address. You can collect matrices on a pre-task and pre-batch basis, or globally apply matrices collection to deploy or to all deployed applications. We can use custom task applications, task demo metrics, and define two different task definitions, task 1 and task 2 with this application. Then you can launch several tasks several times. To obtain the scdf URL when it is deployed in Minikube, run the following command here. In the data flow task execution UI, you should see the following. Open the Grafana dashboard for tasks, you should see the following. Now we are considering Wavefront. Wavefront is a SaaS offering. You need to create a user account first and obtain API-key and Wavefront-URI assigned to account. Follow the general data flow Kubernetes installation instructions. Then add the following properties to a Spring Cloud data flow server configuration. For example, source Kubernetes server config.yaml to enable the Wavefront integration. Then in the Wavefront portal, you should see dashboards similar to those shown in the following image here. Now we are considering Prometheus in CloudFoundry. To configure the data flow server's manifest to send metrics data from stream application to the Prometheus RSockets gateway, follow the manifest-based installation instructions. With Prometheus, Grafana, Spring Cloud data flow, and any other services as defined in the Getting Started CloudFoundry section in the documentation running, you are ready to collect metrics. Depending on where you have installed Grafana, you can access the Grafana dashboard by using the credentials username admin, password. You must provision Grafana with the following task dashboards: scdf-task-batch.json. Now you can deploy the custom task applications and define two tasks, task 1 and task 2. This must be in a single line. You can launch tasks several times. In the data flow task execution UI, you should see the following. Also in the Grafana dashboard for tasks, you should see the following here. Now we are considering Wavefront. Wavefront is a SaaS offering. You need to create user account first and obtain API-key and Wavefront-URI assigned to your account. To configure the data flow servers to send metrics from the stream application to wavefront monitoring system, follow the manifest-based wavefront configuration instructions. Then the wavefront portal, you should see the dashboard similar to those shown in the following image here. Now we are considering InfluxDB. You can follow the general manifest-based installation on CloudFoundry instruction for installing Skipper and Dataflow on CloudFoundry. To enable the task matrix integration, follow the configuration for InfluxDB instructions. Now we are considering monitoring and profiling Spring Boot application. A sample application.properties can have these lines. We can enable Prometheus export by adding the following line to the properties file. Once this line is added, the micrometer will start accumulating data about the application, and this data can be viewed by visiting Actuator Prometheus endpoint. This endpoint would be used in the Prometheus script to fetch data from our application servers. Even though we have added this line in properties, we can't browse Prometheus endpoint since it is disabled by default. We can expose that using management endpoint include Prometheus in the list. Do not enable all endpoints from the actuator, as it can lead to a security loophole. We should choose them selectively, especially in production system. If we want, then do not expose the endpoint to the whole world, as it can expose the whole lot of data about the application. Use some proxy and some rule to hide this from the outside world. The different parts of HTTP requests are customizable, like SLA. Percentile histogram should be computed or not. This is done using metrics.distribution properties. A sample application.properties can have these lines. Enable Prometheus exporter. Enable Prometheus endpoints. Enable percentile based histogram for HTTP requests. HTTP SLA histograms buckets. Enable JVM metrics. As an error example, we can consider this. Prometheus meter registry of type IO micrometer Prometheus meter registry is not eligible to getting processed by the bean processors, etc. Now we are focusing on databases. Here you can see SDN building blocks in Spring Data Neo4j. Here you can see the building blocks. SDN consists of composable building blocks. It builds on top of the Neo4j Java driver. The instance of Java driver is provided by our starter. All configuration options of the driver can be configured through the starter in the namespace org.neo4j.driver. The driver bean provides imperative, asynchronous, and reactive method to interact with Neo4j. You can use all transaction methods provides on that bean, such as auto-commit transaction functions, and unmanaged transaction. Be aware that those transactions are not tied to an ongoing Spring transaction. Integration with Spring data and Spring's platform or reactive transaction manager, such as at Neo4j client. The client is part of SDN, is configured through a separate starter. Spring data Neo4j Spring Boot starter. The configuration namespace of that starter is org.neo4j.data. The client is mapping agnostic. It doesn't know about your domain classes, and you are responsible for mapping a result to an object suiting your needs. The next higher level of abstraction is Neo4j template. It is aware of your domain, and you can use it to query arbitrary domain objects. The template comes in handy in scenarios with a large number of domain classes or custom queries for which you don't want to create an additional repository abstraction each. The highest level of abstraction is Spring Data Repository. All abstractions of SDN come in both imperative and reactive fashions. It is not recommended to mix both programming styles in the same application. The reactive infrastructure requires a Neo4j 4.0 plus database. The template mechanism is similar to the templates of other stores. Find some more information about it. The Neo4j client as such is a unique SDN. The Neo4j client such is unique to SDN. Here you can see SDN Spring Boot starter is provides SDN here. Spring data repositories, Neo4j template, and Neo4j client are inside SDN. Integration with Spring transaction from here on. Spring data repositories are connected to Neo4j template. Neo4j template is connected to Neo4j client. Neo4j client is connected to Neo4j Java driver. Spring Boot starter provides Neo4j Java driver. As an example, we are considering dependencies in Spring Data Commons. In Maven project, you would declare this dependency in the dependency management section in your POM file. Due to the different inception dates of individual Spring Data modules, most of them carry different major and minor version numbers. Easiest way to find compatible ones is to rely on the Spring Data release. Rely on the Spring Data release train BOM. we ship with compatible versions defined. In the Maven project, you would declare this dependency in the dependency management section of your POM file as follows. The current release train version is 2022.0.0. The train version uses Calva with the pattern YY minor and micro. The version name follows $ open brace Calva for close brace Calva. For GA releases and follow the pattern for other versions, $ open brace open curly brace Calva, close curly brace dash $ open curly brace modifier, close curly brace, where modifier can be one of the following: snapshot, current snapshot, M1, M2, and so on, milestones, RC1, RC2, and so on, the release candidates. You can find a working example of using BOMs in BOMs. With that in place, you can declare Spring Data modules you would like to use without a version in the dependencies block as follows. This is declaring a dependency to a Spring Data module. Now we are considering property population in object mapping fundamentals. This is a sample entity. Once an instance of an entity has been created, Spring Data populates all remaining persistent properties of that class. Unless already populated by an entity constructor that is consumed through its constructor argument list, the identifier property will be populated first to allow resolution of cyclic object references. After that, all non-transient properties that have not already been populated by the constructor are set on entity instance. For that, we use the following algorithm. If the property is immutable that but exposes a with method, we use with method to create a new entity instance with the new property value. If property access through getters and setters is defined, we are invoking a setter method. If property is mutable, we set the field directly. If the property is immutable, we are using the construct to be used. We are using the constructor to be used by persistent operations to create copy of the instance. By default, we set the field value directly. Here the identifier property is final, but set to null in the constructor. The class exposes a with id method that's used to set the identifier. For example, when instance is inserted into the data store and an identifier has been generated, the original person instance stays unchanged as new one is created. The same pattern is usually applied for other properties that are store managed but might have to be changed for persistence operations. The wither method is optional, as the persistence constructor is effectively a copy constructor, and setting the property will be translated into creating a fresh instance with a new identifier value applied. To the first name and last name properties are ordinary immutable properties potentially exposed through getters. 3. Age property is an immutable but derived one from the birthday. Birthday property. With the design shown, the database value will trump the defaulting as a string data uses the only declared constructor. Even if the intent is that the calculation should be preferred, it is important that this constructor also takes age as parameter to potentially ignore it, as otherwise the property population step will attempt to set the age field and fail due to it being immutable, and no with method being present. 4. Comment property is mutable, is populated by setting its field directly. 5. The remarks the comment property is here. This is remarks. The remarks property are the remarks properties are mutable and populated by setting the comment field directly. Or by invoking a setter method for. 6. The class exposes a factory method and a constructor for object creation. The core idea here is to use factory methods instead of additional constructors to avoid the need for constructor disambiguation through @persistence creator. Instead, defaulting of properties is handled within a factory method. if you want Spring Data to use the factory method for object instantiation, annotate it with the @persistent creator. Now we are considering core concepts in working with Spring Data repositories. Here you can see a CRUD repository interface. The central interface in the Spring Data repository abstraction is repository. It takes the domain class to manage, as well as the ID type of the domain class as type arguments. This interface acts primarily as a marker interface to capture the types to work with and to help you to discover interfaces that extend this one. The CRUD repository and list CRUD repository interfaces provide sophisticated CRUD functionality for entity class that is being managed. Here this method saves the given entity. This one returns the entity identified by the given ID. Here returns all entities. Returns the number of entities. Here the delete the given entity indicates whether an entity with the given ID exists. List CRUD repository offers equivalent method, but methods but they return list where the CRUD repository methods return an iterable. We also provide persistent technology specific abstractions such as JPA repository and Mongo repository. Those interfaces extend CRUD repository and expose the capabilities of underlying persistence technology in addition to rather generic persistent technology agnostic interfaces such as CRUD repository. Additional to the CRUD repository, there is a paging and sorting repository abstraction that adds an additional methods to easy paginated access to entities. More functionality omitted. Now we are considering interface based projections in projections. Spring data query methods usually return one or multiple instances of the aggregate root managed by the repository. However, it might sometimes be desirable to create projections based on certain attributes of those types. Spring data allows modeling dedicated return types and to more selectively retrieve partial views of managed aggregates. Imagine repository and aggregate roots type such as following example. Now imagine that we want to retrieve the person's name attributes only. What means does Spring data offer to achieve this? The rest of the interface based projections, the easiest way to limit the result of the queries to only the name attributes by declaring interface that exposes accessor methods for the properties to be read, as shown in the following example. The important bit here is that the properties defined here exactly match the properties in the aggregate root. Doing so lets a query method be added as follows. The query execution engine creates a proxy instances of that interface at runtime for each element return and forward calls to expose methods to the target object, declaring method in your repository that override the base method. For example, declared include repository in a store specific interface, or the simple repository result in a call to the base method regardless of the declared return type. Make sure to use compatible return type, as base methods cannot be used for projections. Some store modules support @query annotations to return an overridden base method into a query method that can be used to return projections. Now we are considering a simple considering usage in query by example. A simple example is here. The query by example API consists of 4 parts: probe, the actual example of a domain object with populated fields; example matcher, the example matcher carries details on how to match particular fields. It can be reused across multiple examples. Example, an example consists of probe and the example matcher. It is used to create the query. It also used to create the query. Fetchable fluent query. A fetchable fluent query offers a fluent API that allows further customization of a query derived from an example. Using the fluent API lets you to specify ordering, projection, and result processing for your query. Query by example is well suited for several use cases. Querying your data store with a set of static and dynamic constraints. Frequent refactoring of the domain object without worrying about breaking existing queries. Working independently from the underlying data store API. Query by example also has several limitations. No support for nested or grouped property constraints, such as first name equal question mark 0 or open bracket first name equal question mark 1 and last name question mark 1 and last name equal question mark 2 close bracket. Point 2, next point, only supports start, contains, ends and regress matching for strings and exact matching for other property types. Before getting started with query by example, you need to have a domain object. To get started, create an interface for your repository as shown in the following example. The preceding example shows a simple domain object. You can use it to create create an example. By default, fields having null values. By default, fields having null values are ignored, and strings are matched by using the store specific defaults. Inclusion of properties into query by example criteria is based on nullability. Properties using primitive types int, double, etc. are always included unless the example matcher ignores the property path. Examples can be built by either using the off factory method or by using example matcher. The example is immutable. Following listing shows simple example. Here creates a new instance of the domain object. Here the set the property to the query. Here the create example. You can run example queries by using repositories. To do so, let's your repository interface extend query by example executor T. The following listing shows an expert from query by example executor interface here. Getters and setters omitted here. More functionality omitted. Now we are considering annotation based auditing metadata in basics in auditing. You can see here an audited entity. We provide at created by and at last modified by to capture the user who created or modified the entity, as well as at created date and at last modified date to capture when the change happened. As you can see, the annotations can be applied selectively depending on which information you want to capture. The annotations indicating to capture when the change is made can be used on properties of type JDK8 date and time types, long, capital L long, and legacy Java date and calendar. Auditing metadata does not necessarily need to live in the root level entity, but can be added to an embedded one depending on the actual store in the use. As shown in the snippet below here. Further properties omitted. Further properties omitted. Now we are focusing on database backends. This is pom.xml. The Vault supports several database secret backends to generate database credentials dynamically based on configured roles. This means services that need to access database no longer need to configure credentials. They can request them from Vault and use Vault's leasing mechanism to more easily roll keys. Spring Cloud Vault integrates with this backend database: Apache Cassandra, Couchbase database, Elasticsearch, MongoDB, MySQL, PostgreSQL. Using a database secret backend requires to enable the backend in the configuration and Spring Cloud Vault config databases dependency. Vault ships since 0.7.1 with dedicated database secret backend that allows database integration via plugins. You can use that specific backend by using the generic database backend. Make sure to specify appropriate backend path. For example, spring.cloud.vault.mysql.role.backend equal database. Here you can see the example pom.xml. Enabling multiple JDBC compliant databases will generate credentials and store them by default in the same property keys. Hence, property names for JDBC secrets need to be configured separately. Now we are considering database. You can configure the property names by setting spring.cloud.vault.database.username-property and spring.cloud.vault.database.password-property. Spring Cloud Vault can obtain credentials from any database listed in www.vaultproject.io/API/secret/databases/index.html. Integration can be enabled by setting spring.cloud.vault.database.enabled equal true, default false, and providing the role name with spring.cloud.vault.database.role equal etc. While database backend is a generic one, spring.cloud.vault.database specifically targets JDBC databases. Username and passwords are available from spring.datasource.username and spring.datasource.password properties. So using Spring Boot will pick up the generated credentials for your data source without further configuration. You can configure the property names by setting spring.cloud.vault.database.password-property database.username-property and spring.cloud.vault.database.password-property. Username and passwords are available from spring.datasource.username and spring.datasource.password properties. Now we are considering multiple databases. Make sure to configure username-property and password-property appropriately. Sometimes credentials for a single database isn't sufficient because an application might connect to two or more databases of same kind. Beginning with version 3.0.5, the Spring Vault supports the configuration of multiple database secret backends under the spring.cloud.vault.databases asterisk namespace. The configuration accepts multiple database backends to materialize credentials into specified properties. Make sure to configure username-property and password-property appropriately. Name, descriptive name of the database configuration. Name.enabled. Setting this value to true enables the database backend config usage. Name.role sets the role name of the database role definition. Name.backend sets the path of the database mount to use. Username-property sets the property name in which the database username is stored. Make sure to use unique property names to avoid property shadowing. Name.password-property sets the property name in which the database password is stored. Make sure to use unique property names to avoid property shadowing. Spring Cloud Vault does not support getting new credentials and configuring your data source with them when maximum lease time has been reached. That is, if max underscore TTL of the database role in the vault is set to 24H, that means that 24 hours after your application has started, it can no longer authenticate with the database. Now we are considering Apache Cassandra. Apache Cassandra. You can configure the property names by setting Spring Cloud Vault Cassandra username dash property and Spring Cloud Vault Cassandra dot password dash property. Cassandra backend has been deprecated in Vault 0.7.1 and it is recommended to use the database backend and mount it as Cassandra. Spring Vault can obtain credentials for Apache Cassandra. The integration can be enabled by setting spring.cloud.vault.cassandra.enabled equal true, default false, and providing the role name with spring.cloud.vault.cassandra.role equal etc. Username and passwords are available from spring.data.cassandra.username and spring.data.cassandra.password properties. So using Spring Boot will pick up the generated credentials without further configuration. You can configure the property names by setting spring.cloud.vault.cassandra.username dash property and spring.cloud.vault.cassandra.password dash property. Enabled, setting this value to true enables the Cassandra backend config usage. Role sets the role name of the Cassandra role definition. Backend sets the path of the Cassandra mount to use. Username dash property sets the property name in which the Cassandra username is stored. Password dash property sets the property name in which the Cassandra password is stored. Now we are considering couch-based database. You can configure the property names by setting spring.cloud.vault. Couchbase.username dash property and spring.cloud.vault.couchbase dash property. Spring Cloud Vault can obtain credentials for Couchbase. Integration can be enabled by setting spring.cloud.vault.couchbase.enabled equal true, default false, and providing the role name with spring.cloud.vault.couchbase.role equal etc. Username and passwords are available from spring.couchbase.username and spring.couchbase.password properties. So using Spring Boot will pick up the generated credentials without further configuration. You can configure the property names by setting spring.cloud.vault.couchbase.username dash property and spring.cloud.vault.couchbase.password dash property. Enabled, setting this value to true enables the Couchbase backend config usage. Role sets the role name of the Couchbase role definition. Backend sets the path of the Couchbase mount to use. username dash property sets the property name in which the Couchbase username is stored. Password dash property sets the property name in which the Couchbase password is stored. Now we are considering Elasticsearch. You can configure the property names by setting spring.cloud.elasticsearch username dash property and spring.cloud.vault.elasticsearch.password dash property. Spring Cloud Vault can obtain since version 3.0 credentials for Elasticsearch. The integration can be enabled by setting spring.cloud.vault.elasticsearch.enabled equal true, default false, and providing the role name with spring.cloud.vault.elasticsearch.role equal etc. Username and passwords are available from spring.elasticsearch.rest.username and spring.elasticsearch.rest.password properties. So using Spring Boot will pick up the generated credentials without further configuration. You can configure the property names by setting spring.cloud.vault.elasticsearch.username dash property and spring.cloud.vault.elasticsearch.password dash property. Enabled setting this value to true enables the Elasticsearch backend config usage. Role sets the role name of the Elasticsearch role definition. Backend sets the path of Elasticsearch mount to use. Username dash property sets the property name in which the Elasticsearch username is stored. Password dash property sets the property name in which the Elasticsearch password is stored. Now we are considering MongoDB. You can configure the property names by setting spring.cloud.vault.mongodb.username dash property and spring.cloud.vault.mongodb.password dash property. The MongoDB backend has been deprecated in Vault 0.7.1 and it is recommended to use database backend and mount it as MongoDB. Spring Cloud Vault can obtain credentials for MongoDB. Integration can be enabled by setting spring.cloud.vault.mongodb.enabled equal true, default false, and providing the role name with spring.cloud.vault.mongodb.role equal etc. Username and passwords are stored in spring.data.mongodb.username and spring.data.mongodb.password. So using Spring Boot will pick up the generated credentials without further configuration. You can configure the property names by setting spring.cloud.vault.mongodb.username dash property and spring.cloud.vault.mongodb.password dash property. Enabled setting this value to true enables MongoDB backend config usage. Role sets the role name of the MongoDB role definition. Backend sets the path of the MongoDB mount to use. Username property sets the property name in which the MongoDB username is stored. Password dash property sets the property name in which the MongoDB password is stored. Now we are considering MySQL. You can configure the property names by setting spring.cloud.vault.mysql.username dash property and spring.cloud.vault.mysql.password dash property. MySQL backend has been deprecated in Vault 0.7.1, and it is recommended to use database backend and mount it as MySQL. Configuration for cloud.vault.mysql will be removed in future version. Spring Cloud Vault can obtain credentials for MySQL. The integration can be enabled by setting spring.cloud.vault.mysql.enabled equal true, default false, and providing the role name with spring.cloud.vault.mysql.role equal etc. Username and passwords are stored in spring.datasource.username and spring.datasource.password properties. So using Spring Boot will pick up the generated credentials without further configuration. You can configure the property names by setting spring.cloud.vault.mysql.username-property and spring.cloud.vault.mysql.password-property. Enabled setting this value to true enables the MySQL backend config usage. Role sets the role name of the MySQL role definition. Backend sets the path of the MySQL mount to use. Username-property sets the property name in which the MySQL username is stored, and password-property sets the property name in which the MySQL password is stored. Now we are considering PostgreSQL. You can configure the property names by setting spring.cloud.vault.postgresql.username-property and spring.cloud.vault.postgresql.password-property. The PostgreSQL backend has been deprecated in Vault 0.7.1, and it is recommended to use database backend and mount it as Postgres. Configuration for spring.cloud.vault.postgres will be removed in future version. Spring.cloud.vault can obtain credentials for PostgreSQL. Integration can be enabled by setting spring.cloud.vault.postgresql.enabled equal true, default false, and providing the role name with spring.cloud.vault.postgres.role equal etc. Username and passwords are available from spring.datasource.username and spring.datasource.password. So using Spring Boot will pick up the generated credentials without further configuration. You can configure the property names by setting spring.cloud.vault.postgresql.username equal username-property and spring.cloud.vault.postgres.password-property. Enabled setting this value to true enables the Postgres backend config usage. Role sets the role name of the Postgres role definition. Backend sets the path of the PostgreSQL mount to use. Username-property sets the property name in which the Postgres username is stored, and password-property sets the property name in which the Postgres SQL password is stored. Now we are considering database and schema admin in Spring Data Cloud Spanner. Databases and tables can be database and tables inside Spanner instances can be created automatically from Spanner persistent entity objects. The interface Spanner persistent entity T Cloud Spanner specific interface for mutable persistent entity stored in a cloud spanner table. This is in the package org.springframework.cloud.gcp.data.spanner.core.mapping. Schemas can be generated for entire object hierarchies with interleaved relationships and composite keys. The Boolean parameter indicates that the database will be created if it does not exist. Now we are considering configuring the lattice connector in connecting to Redis in Spring in Redis support in Spring Data Redis. The following example shows how to create a new lattice connection factory. Lattice is a Netty based open source connector supported by Spring Data Redis through the org.springframework.data.redis.connection.lattice package. Add the following to the pom.xml files dependencies element. The following example shows how to create a new lattice connection factory. There are also few lattice specific connection parameters that can be tweaked. By default, the lattice connection, all lattice connection instances created by the lattice connection factory share the same thread safe native connection for all non-blocking and non-transactional operations. To use the dedicated connection each time, set the share native connection to false. Lattice connection factory can also be configured to use lattice pool for pooling blocking and transactional connections for all connections. If share native connection is set to false, Lattice integrates with Lattice native transports, letting you use the Unix domain sockets to communicate with Redis. Make sure to include appropriate native transport dependencies that match the runtime environments. Other dependency elements omitted. Now we are considering fundamentals in repository resources in Spring Data REST. Consider the following repository interface. The core functionality of Spring Data REST is to export resources for Spring Data repositories. Thus, the core artifact to look at and potentially customize the way the exporting works is the repository interface. Consider the following repository interface. For this repository, Spring Data REST exposes a collection resource at /orders. The path is derived from the uncapitalized pluralized simple class name of the domain class being managed. It also exposes an item resources for each of the items managed by repository under URI template /orders/id. By default, the HTTP methods to interact with these resources map to the according methods of the CRUD repository. This is an example usage. Now we are considering names, Spring namespace in Sol repositories in Spring data for Apache Sol. So here you can see the embedded Sol server using the namespace. The Spring Data Sol module contains a custom namespace that allows definition of repository beans that has element instantiating Solr client. Using the repository element looks up the Spring Data repositories as described in creating repository instances in the documentation. If you can add solr repositories, then base dash package equal double quotation com.acme dot repositories double quotation. This following example shows how to set up embedded Sol server. Here you can see annotation based configuration. The Spring Data Sol repositories support can be activated both through an XML namespace and by using an annotation through Java configuration. The following example shows how to set up Sol repositories with Java configuration. The preceding configuration sets up an this example sets the set up the embedded Sol server, which is used by the Sol template. Spring Data Sol repositories are activated by using the @enabled Sol repository annotation, which essentially carries the same attributes as the XML namespace. If no base package is configured, it uses the package in which the configuration class resides. Here you can see the here you can see the using CDI to set up Sol repositories. You can use CDI to set up Spring Data Sol repositories. As the following example shows here. Now we are considering Spring XML configuration in Apache data. Spring data for Apache Geode repositories. To bootstrap Spring data repositories, use repositories element from the Spring data for Apache Geode data namespace, as for following example shows. This configuration snippet looks for interfaces below the configured base package and create repository instances for those interfaces backed by a simple Gemfire repository. Bootstrap process fails unless you have your application domain classes correctly mapped to configured regions. Spring Java-based configuration. Alternatively, many developers prefer to use Spring Java-based container configuration. Using this approach, you can bootstrap Spring data repositories by using the SDG enable Gemfire repositories annotation, as the following example shows here. Rather than use the base packages attributes, you may prefer to use the type-safe base package classes attributes instead. Base package classes lets you to specify the package that contains all your application repository classes by specifying only one of your application repository interface types. Consider creating a special no-op marker class or interface in which package that serves no purpose other than to identify the location of the application repository is referenced by this attribute. In addition to the package base packages and base package classes attributes like Spring's component scan annotation, the enable Gemfire repositories annotation provides include and exclude filters based on Spring's component scan.filter type. You can use the filter type attributes to filter by different aspects, such as whether an application repository type is annotated with a particular annotation or extend a particular class type, so on. The enabled Gemfire repository annotation also lets you to specify location of the named OQL queries which reside in Java properties file by using the named queries location attributes. Property name must match the name of the repository query method, and property values is the OQL query you want executed when the repository queries method is called. The repository implementation postfix attribute can be set to an alternate values default to IMPL if your application requires one or more custom repository implementations. This feature is commonly used to extend Spring Data repository into infrastructure to implement a feature not provided by the data store, for example is SDG. One example of where custom repository implementations are needed with the Apache Geode is when performing joins. Joins are not supported by SDG repositories. With the Apache Geode partition region, the join must be performed on collocated partition regions. Since Apache Geode does not support distributed joins, in addition to the equi-join OQL query must perform inside the Apache Geode function. Many other aspects of the SDG's repository infrastructure extension may be customized as well. Now we are considering declaring Spring data repositories in create your domain in getting started in Spring Data Neo4j. A reactive repository fitting to any of the movie entities above look like this. You basically have two options here. You can work in a ISO agnostic fashion with SDN and make your domain specific extend one of org.spring framework.data.repository next org.spring framework.data.repository.crude repository or org.spring framework.data.repository.reactive crude repository and org.spring framework.data.repository.reactive shorting repository. Choose imperative and reactive accordingly. While technically not prohibited, it is not recommended mixing imperative and reactive database access in the same application. We won't support you with scenarios like this. The other option is to settle on store specific implementation and gain all the methods we support out of the box. The advantage of this approach is also the biggest disadvantage. Once out, all those methods will be part of your API. Most of the time, it is harder to take something away than to add stuff afterwards. Furthermore, using store specific leaks your store into your domain for a performance point of view, there is no penalty. Reactive repository fitting of any of the movie entities above like this. Testing reactive code is done with reactor.test.step verifier. Now we are considering configuration using the traditional bean element in Oracle pooling data source. We will start by looking at the very basic data source configuration using traditional bean element. Here the here we specify data source implementation class as the Oracle data source. Here we specify the URL using the URL property. Note that it is uppercase in the implementation while it is lowercase in the most other data source implementations. Here the username is specified using the user property. Here the password is specified using the password property. Here the connection caching must be enabled explicitly using the connection caching enabled property. Property placeholders will be filled using this context property placeholder element from the context namespace. Now we are considering using Spring, using the Spring for Apache Hadoop Java config in Hadoop configuration in Spring Data JDBC extensions. Annotation-based configuration is designed to work via Spring Hadoop configuration adapter, which is loosely trying to use the same type of DSL language familiar from XML. Within the adapter, you need to override the configure method, which is exposing Hadoop configurer containing familiar attributes to work with Hadoop configuration. At enable, Hadoop annotation is required to mark Spring at configuration class to be a candidate for Spring Hadoop configuration. In addition to with configuring Hadoop, in addition to referencing configuration resources, one can tweak Hadoop settings directly through Java properties here. This can be quite handy when just a few options need to be changed. As an example, we can consider fail to configure a data source URL attribute is not specified and no embedded data source could be configured. Now we are considering message brokers. Here you can see an architecture of a typical Spring Cloud Stream microservice. Following figure figure shows an architecture of typical Spring Cloud Stream microservice. A source would only have an input channel. The processor would have both input and output channel. A sink would have only an output channel. Applications declare what kind of connection they would want, an input and or an output. Spring Cloud Stream will establish all that would be needed to connect applications over the message broker. The Spring Cloud Stream would do the following: inject input and or output channels into applications, establish connections with the message brokers through a message equal broker specific binder. Binders bring configurability to Spring Cloud Stream applications. A Cloud Stream application only declares the channels. Deployment team can configure at runtime which message broker, Kafka or RabbitMQ the channels connect to. Spring Cloud Stream uses auto configuration to detect the binder available on the class path. to connect to a different message broker, all that we need to do is to change the dependency of the project. Another option is to include multiple binders in the class path and choose the one to use at runtime. Here you can see source, processor, and sync stream map. Here you can see application logic and the input channels and output channels. Application logic interacts with binders. Binders interact with applications and message broker here. Here you can see producers and consumers in binders. The following image shows the general relationships of producers and consumers. A producer is any component that sends messages to a channel. The channel can be bound to an external message broker with the binder implementation. Of that broker. When invoking bind producer method, the first parameter is the local channel. The first parameter is the name of the destination within the broker. The second parameter is the local channel instance to which the producer sends the message. And the third parameter contains the properties such as a partition key expression to be used within the adapter that is created for that channel. The consumer of any a consumer is any component that receives the messages from a channel. As with the producer, the consumer's channel can be bound to an external message broker. When invoking bind consumer method, the first parameter is the destination name, and the second parameter provides the name of the of a logical group consumers. Each group that is presented by consumer bindings for a given destination receives a copy of each message that the producer sent to that destination. That is, it follows normal publish subscribe semantics. If there are multiple consumer instances bound with the same group name, then the messages are load balanced across the consumer instances so that each message sent by a producer is consumed by only a single consumer instance within each group. That is, it follows a normal queue semantics. Here you can see bind producer is connected to the channel. Bind producer foo output channel properties, and here you can see the broker, and channel is connected to the bind consumer here. Foo default input channel properties. Here the bind consumer foo wire trap channel input channel properties. Now we are considering introducing Spring Cloud Stream. The following example shows a sync application that receives external messages. Spring Cloud Stream is a framework. The annotation type enables the binding of target annotated with input and output to a broker according to a list of interfaces passed as value to the annotation. This is in the package org.spring framework.cloud.spring-stream.annotation. Spring Cloud Stream is a framework for binding message-driven microservice applications. Spring Cloud Stream builds upon Spring Boot to create standalone production-grade Spring applications and uses Spring integration to provide connectivity to message brokers. It provides opinionated configuration of middleware from several vendors, introducing the concept of persistent publish subscribe semantics, consumer groups, and partitions. You can add enable binding annotation to your application to get immediate connectivity to a message broker. And you can add stream listener to a method to cause it to receive events for stream processing. The following simple sync application which receives external messages. The enable binding annotation takes one or more interfaces as parameters. In this case, the parameter is a single sync interface. An interface declares input or an interface declares input and or output channels. The Spring Cloud Stream provides interfaces source, sync, and processor. You can also define your own interfaces. The following is the definition of the sync interface. The at input annotation identifies an input channel through which received messages enter the application. The at output annotation identifies an output channel through which the published messages leave the application. The at input and at output annotations take a channel name as a parameter. If a name is not provided, the name of the annotated method will be used. The Spring Cloud Stream will create an implementation of the interface for you. You can use this application by auto-wiring it as in the following example of a test case. Now we are considering class path detection in binder detection. For example, a Spring Cloud Stream project that aims to bind only to RabbitMQ can simply add the following dependency. The artifact Spring Cloud Stream binder Rabbit, the RabbitMQ binder implementation. By default, Spring Cloud Stream relies on Spring Boot auto configuration to configure the binding process. If a single bind implementation is found in the class path, Spring Cloud Stream automatically uses it. For example, Spring Cloud Stream project that aims to bind only to RabbitMQ can add the following dependency. More specific Maven coordinates of other binding dependencies. See the documentation for that binder implementation. Now we are considering multiple binders on the class path. For instance, a processor application that has channels with the names input and output for read write respectively, which read from Kafka and writes to RabbitMQ can specify the following configuration. When multiple binders are present on the class path, the application must indicate which binder to be used for each channel binding. Each binder configuration contains meta-inf/spring.binders file, which is a simple properties file as shown in the following example here. Similar files exist for other provided bind implementations such as Kafka, and custom bind implementation are expected to provide them as well. The key represent and identify the name for bind implementation, whereas the value is comma separated list of configuration classes that each contain one and only one bean definition of type. org.springframework.cloud.stream.binder.binder. Binder selection can either be performed globally using spring.cloud.stream.default binder property. For example, spring.cloud.stream.default binder equal rabbit, or individually by configuring the binder on each channel binding. For instance, a processor application that has channels named input and output for read and write respectively, that reads from Kafka and writes to RabbitMQ can specify the following configuration. Now we are considering connecting to multiple systems. For example, this is the typical configuration for a processor application which connects to two RabbitMQ broker instances. By default, binders share the application's Spring Boot auto configuration, so that one instance of each binder found on the class path created. If your application should connect to more than one broker of the same type, you can specify multiple binder configurations each with the different environment settings. Tuning an explicit binder configuration disables the default binder configuration process altogether. If you do so, all binders in use must be included in the configuration. The framework that intend to use the Spring Cloud Spring transparently may create bind a configuration that can be referenced by name, but they do not affect the default binder configuration. In order to do so, a binder configuration may have default candidate flag set to false. For example, spring.cloud.stream.binders, then configuration name dot default candidate, you cannot see here, equal false. This denotes the configuration that exists independently of the default binder configuration process. The following example shows typical configuration for a processor that connects to two RabbitMQ broker instances. Now we are considering binding, visualization and control. We're focusing on visualization. Once those then you should see the following logs when application starts. Since version 2.0, Spring Cloud Stream supports visualization and control of binding through actuator endpoints. Starting with version 2.0 actuator and the web are optional, and you must first add one of the web dependencies as well as add the actuator dependency manually. You can add Spring boot starter, Spring dash boot dash starter dash web artifact. For the web flux, you can add Spring dash boot dash starter dash web flux artifact, and for the actuator dependency, you can add Spring dash boot dash starter dash actuator artifact. To run the Spring Cloud Stream 2.0 apps, the CloudFoundry, in CloudFoundry you must add Spring dash boot dash starter dash web and Spring dash boot dash starter dash actuator to the class path. Otherwise, the application will not start due to health check failures. You must enable the binding actuator endpoint by setting the following property dash dash management dot endpoints dot web dot exposure dot include equal bindings. Once those prerequisites are satisfied, you should see the following in logs when the application starts. To visualize the current binding, access the following URL here, and to visual alternatively this is http //host :port/actuator /binding. The alternative to see the to see a binding, access the one of the URLs similar to the following: http //host :port /actuator /binding /my binding name. Now we are considering binder configuration properties. They must be prefixed with spring.cloud.stream.binders then configuration name. Here the binder type. The following properties are here the binder type. It typically references one of the binders found on the class path, in particular a key in meta-ina /spring.binders file. By default, it has the same value as the configuration name. Now we are considering customizing the message broker. There are convenient starters for the bus with AMQP, RabbitMQ, and Kafka, the Spring Cloud starter bus, AMQP or Kafka here. Spring Cloud Bus uses Spring Cloud Stream to broadcast the messages. So to get message to flow, you need only include the bind implementation of your choice in the class path. There are convenient starters for the bus with AMQP, RabbitMQ, and Kafka. Generally speaking, Spring Cloud Stream relies on Spring Boot auto-configuration conventions for configuring middleware. For instance, the AMQP broker address can be changed with spring.rabbitmq. Configuration properties. Spring Cloud Bus has a handful of native configuration properties in spring.cloud.bus *. For example, spring.cloud.bus.destination is the name of the topic to use as the external middleware. Normally, the default suffix. Now we are focusing on config server. Spring Cloud config server provides an HTTP resource-based API for external configuration, name-value pairs, or equivalent YAML content. The server is embeddable in Spring Boot application by using the @enable config server annotation. Here you can see Spring Cloud config architecture, config server architecture. Here is a simple diagram of config server architecture. Let's dive into the config server architecture diagram. The configuration properties of application is kept on a data store such as JIT database or some other kind of data store, data source. The default data store is configured to Git via Spring auto configuration and can be configured to some other data stores such as RDBMS. Config server reads the application properties from the data store and serves them to clients. Config clients are configured to read the properties, read the application properties from the config server instead of from the local properties file. When the Spring Boot client application is bootstrapped, it requests the properties from the config server and loads them all into the property sources in the Spring application context as the key values. These key values become accessible via Spring's environment interface to other Spring components, just as in the Spring property management you already know and can be used as auto-wiring environment variables. Auto-wiring environment interface using @value annotation, using @configuration properties. Here you can see config client is inside microservice 1 instance 1 here, and here instance n, and these instances are service 1 instances are inside API 1, and service 2 instances are inside API 2, and config client is inside service here microservice 2 instance 1, and here the config client is inside microservice 2 instance n, and APIs are connected to config server, dev, test, product, production. and config server is connected to data store, JIT, DB, and other data store are inside the data store. Here you can see a high availability architecture for config server. Config server requires high availability since the services won't be able to bootstrap if the config server is not available. Hence, redundant config servers are required for high availability. However, the applications can continue to run if the config server is unavailable after services are bootstrapped. In this case, services will run with the last known configuration states. Hence, the config server availability is not at the same critical level as the microservices availability. In order to make the config server highly available, we need multiple instances of the config server. Since the config server is stateless HTTP service, multiple instances of configuration servers can be run in parallel. Based on the load on the configuration server, a number of instances have been adjusted. The bootstrap.properties is not capable of handling more than one server address. Hence, multiple configuration servers should be configured to run behind the load balancer or behind a local DNS with failover and fallback capability. The load balancer or DNS server URL will be configured in the microservices bootstrap.properties. This is with the assumption that the DNS or load balancer is highly available and capable of handling failovers. In a production scenario, it is not recommended to use local file-based JIT repository. The configuration server should be typically backed with a high available JIT service. This is possible by either using an external highly available JIT service or highly available internal JIT service. SVN can also be considered. Having said that, the already bootstrap config server is always capable of working with a local copy of the configuration. Hence, we need a highly available Git only when the config server needs to be scaled. Therefore, this is not as critical as microservices availability or config server availability. RabbitMQ also has to be configured for high availability. High availability for RabbitMQ is needed only to push configuration changes dynamically to all instances. Since this is more of an offline controlled activity, it does not really require the same high availability as required by the components. RabbitMQ high availability can be achieved by either using a cloud service or a locally configured highly available RabbitMQ service. Config server config client 1 is connected to load balancer through HTTP // HA domain. Config client 2 is connected to load balancer through HTTP // config HA domain. Config client 3 is connected to load balancer through HTTP config config HA domain. Load balance is connected to config server 1 through HTTP // server 1 here. Load balance is connected to config server 2 through http colon / server 2 here. Config server 1 and config server 1 and config server 2 is are connected to Git repository. Config server 1 and config server 2 are connected to RabbitMQ here. Here you can see the refreshable configuration using Cloud Config Server, Spring Cloud Bus, and RabbitMQ and Git. Here config server plus Spring Cloud Bus read properties. Here the client application fetches config properties from to config server plus Spring Cloud Bus, and client applications subscribes to RabbitMQ in step 2 here. And here 3 git push config file. Here for webhook post / monitor to config server plus Spring Cloud Bus. 5 config server plus Spring Cloud Bus sends refresh event to RabbitMQ. Step 7 cloud application listen to refresh event from RabbitMQ. Here step 7 client application fetches config properties from Spring config server plus config cloud bus. This is a sample architecture here. As an example, we are considering stand up a config server in centralized configuration. Following listing is from configuration-service /source src /main /java /com /example /configuration services /configuration service application.java shows such an application here. You first need to a config service to act as a sort of intermediary between your Spring application and a typically version control repository of configuration files. You can use Spring Cloud's at enable config server to stand up a config server that can communicate with other applications. This is a regular Spring Boot application with an with one annotation added to enable the config server. The following listing is from this path. Config server needs to know which repository to manage. There are several choices here, but it starts with a Git based file system repository. You could as easily point the config server to a GitHub or GitLab repository. On the file system, create a new directory and run git init in it. Then add the file called beautiful-client.properties to the Git repository. Then run git commit init. Later you will connect to the config server with the Spring Boot application whose application.name property identifies it as beautiful-client to the config server. This is how the config server knows which set of configuration to send to a specific client. It also send all the values from any file name application.properties or application.yml in the Git repository. Property keys in more specifically named file such as a-beautiful-client dot properties, override those in application dot properties, so application dot yml. Add a simple property name and value message equal hello world to the newly created a dash beautiful dash client dot properties file, and then git commit the change. Specify the path to the git repository by specifying spring.cloud.config server.git.uri property in configuration dash services /src /main services /resources application dot properties. You must also specify a different server dot port value to avoid port conflict when you run both this server and another Spring Boot application in the same machine. Following listing is from configuration dash service /src /main resources application dot properties. So such an application dot properties file here. This example use a file based git repository at $ forts open curly brace home close curly brace home /desktop /config. You can create one easily by making a new directory and running a git commit command on the properties and YAML files in it. Following set of commands does this work. Or you could use a remote git repository such as GitHub if you change the configuration file in the application to point to that instead. Now we are considering a reading configuration from the config server by using a config client. Now that you have stood up a config server, you need to stand up a new Spring Boot application that uses config server to load its own configuration and refreshes its configuration to reflect changes to the config server on demand without restarting the JVM. To do so, at the org.springframework.cloud spring-cloud-starter-config dependency to connect to this config server. Spring sees the configuration property files as it would any property file loaded from application.properties or application.yml or any other property source. The properties to configure the config client can be set up in the usual way for Spring Boot application. Specify the client spring.application.name as here a bootful client here, and the location of the config server spring.config.import in configuration dash client /source /main resources application.properties. The following listing shows that file here. You also want to enable /refresh endpoint to demonstrate dynamic configuration changes. Listing above shows how to do via the management.endpoint.web.exposure include property. The application can access any value in the config server by using traditional mechanisms such as at configuration properties, so at value open brace, open bracket, double quotation, dollar sign, open brace, then etc. Then close brace, close curly brace, double quotation, and close bracket, or through the environment abstraction. Now you need to create a Spring MUC REST controller that returns the resolved message property value. By default, the configuration values are read from on the client's startup and not again. You can force to bean to refresh its configuration, that is to pull updated values from the config server by annotating message REST controller with the Spring Cloud config at refresh scope, and then triggering the refresh event. The following listing is from configuration -client /src /main /java /conf /example /configuration client /configuration client application.java. This is how to do so here. We set management.endpoint.web.exposure.include equal * in the client application to make this is easy to test. Since System Boot 2.0, the activator endpoints are exposed by default. By default, you can still access them over JMX if you do not set the flag. Now we are considering test the application. You can test the end-to-end result by starting the config server first, and then once it is running, starting the client, visit the client app in the browser at http://localhost:8080/message. There you should see the hello world in the response. Change the message key in the bootful client.properties a-beautiful-client.properties file in the Git repository. So to do something different, hello Spring, perhaps you can confirm that the config server sees the change by visiting http://localhost:8080/a-beautiful-client/default. You need to invoke the refresh Spring Boot activator endpoint in order to force the client to refresh itself and draw in the new value. Spring Boot's activator exposes operational endpoints such as health checks and environment information about an application. To use it, you must add org.springframework.boot :spring-boot-starter-activator to the client applications class path. You can invoke the refresh activator endpoint by sending an empty HTTP post to the client's refresh endpoint, http ://localhost :8080/activator/refresh. Then you can confirm it worked by visiting the http :// colon 8080 / message endpoint. Following command invokes the activator refresh command. As an example too, we can consider the package org.springframework.cloud.config.server. In Spring Cloud's config server, consequently, the following application is a config server. The annotation type enable config server is in package org.springframework.cloud.config.server. Now we are considering environment repository. Environment repository, where should you store the configuration data for config server? The strategy that governs the behavior is the environment repository. Serving environment objects. The environment is a shadow copy of the domain from Spring environment, including property sources as the main feature. The environment resources are parameterized by 3 variables: application, which maps the spring.application.name on the client side; profile, which maps the spring.profiles.active on the client, comma separated list; label, which is a server side feature labeling a versioned set of config files. Repository implementation generally behave like a Spring Boot application, loading configuration files from spring.config.name equal to the application parameter, and the spring.profiles.active equal to the profiles parameter. Precedence rules for profiles are also the same as in a regular Spring Boot application. Active profiles take precedence over default, and if there are multiple profiles, the last one wins, similar to adding entries to a map. And here there you can see the interface environment repository, which is in the package org.springframework.cloud.config.server.environment. Here you can see a pattern matching and multiple repositories in Git. Spring Cloud Config also includes support for more complex requirements with pattern matching on the application and profile names. The pattern format is a comma separated list of application / profile names with wildcards. Note that the pattern beginning with the wildcard may need to be quoted. Here, if the application / profile does not match any of the patterns, it uses the default URI defined under spring.cloud.config.server.git.uri. In pattern property, in repo is actually an array. If you can use YAML array or 0, 1, etc. suffices the property files to bind to multiple patterns. You may need to do so if you are going to run apps with multiple profiles, as shown in the following example here. Spring Cloud guesses a pattern containing a profile that does not ends with in the asterisk implies that you actually want to match a list of profile staging with pattern. So asterisk / staging is a shortcut for asterisk / staging, asterisk / staging, comma asterisk, and so on. This is a common where, for instance, you need to run applications in the development profile locally, but also the cloud profile remotely. Now we are focusing health indicator. You can configure the health indicator to check more application along with the custom profiles and custom labels, as shown in the following example. Config server comes with the health indicator that checks whether the configured environment repository is working. By default, it asks the environment repository for an application named app, the default profile and the default label provided by environment repository implementation. You can configure the health indicator to check more applications along with the custom profiles and custom labels. as shown in the following example here. You can disable the health indicator by setting Spring Cloud by setting management.health.config.enabled equal false. You can also provide a custom down status of your own by setting the property spring.cloud.config.server.health, then .down dash health dash status value to down by default. Now we are considering security. To use the default Spring Boot configured HTTP basic security, include Spring security on the class path, for example, through Spring Boot starter security, spring-boot-starter-security. It's a Spring Boot starter security starter for using Spring security. You can secure your config server in any way that makes sense to you, from physical network security to auth to bearer tokens, because Spring Security and Spring Boot offers support for many security arrangement. To use the default Spring Boot configured HTTP basic security, include Spring security on the class path, for example, through spring-boot-starter-security. The default is a username of user and a randomly generated password. A random password is not useful in practice, so we recommend you configure the password by setting spring.security.user.password and encrypt it. Now we are considering actuator and security. If the actuator is not a dependency of config server, request to /actuator/ would be match the config server API /application/label, possibly leaking security information. Some platforms configure health checks for some or some similar and point to /actuator/health or other actuator endpoints. If the actuator is not a dependency of config server, request to /actuator/ would match the config server API /application/label, possibly leaking secure information. Remember to add the spring-boot-starter-actuator dependency in this case and configure the users, such as the user that makes call to /actuator/ does not access to the config server API at /application/label. Now we are considering encryption and decryption. If you set up a remote config repository for config client applications, it might contain an application.yml similar to the following. To use encryption and decryption features, you need the full strength of JC installed in your JVM. It is not included by default. You can download the Java cryptography extension JCE unlimited strength jurisdiction policy files from Oracle and follow the installation instruction. Essentially, you need to replace the two policy files in the JRE lib/security directory with ones that you downloaded. If the remote property sources contain encrypted content values starting with cipher, here curly brace cipher closing curly brace, they are decrypted before sending to client over HTTP. The main advantage of this setup is that the property values need not to be in plain text when they are at rest, for example in a Git repository. If the value cannot be decrypted, it is removed from the property source and an additional property is added with the same key but prefixed with invalid and value that means not applicable, usually NA. This is largely to prevent cipher text being used as a password and accidentally leaking. If you set up a remote config repository for config client application, it might contain application.yml similar to the following. encrypt values in application.properties. File must not be wrapped in quoted, otherwise the value is not decrypt. The following example shows values that would work. You can safely push this plain text to a shared Git repository and the secret password remain protected. This is application.yml and this is application.properties. The server also exposes /encrypt and /decrypt endpoints on the assumption that these are secured and only accessed by authorized agents. If you edit the remote config file, you can use the config server to encrypt values by posting to the /encrypt endpoint as shown in the following example. If you are testing with CURL, then use --data -URL encode instead of -d and the prefix the value to the encrypt with equal sign. Curl requires this, or set an explicit content -type text /plain to make sure the CURL curl encodes the data correctly when there are special characters. Plus is particularly tricky. Be sure not to include any of the curl command statistics in the encrypted value. This is why the example use -s option to silence them. Outputting the value to a file can help avoid this problem. Inverse operation is also available through /decrypt, provided the server is configured with a symmetric key and a fully or a full key pair, as shown in the following example. Take the decrypt value, take the encrypt value and add the cipher at the open curly brace cipher close curly brace prefix before you put it into the YAML or properties file and before you commit and push it to a remote potentially insecure store. /encrypt /decrypt endpoints also both accept paths in the form of /application/profiles, which can be used to control cryptography on a per application name and per profile basis when clients call into the main environment sources. To control the cryptography in this granular way, you must also provide @bean of type text encryptor locator that creates a different encryptor per name and profiles. The one that is provided by default does not do so. All encryptions use the same key. Now we are considering creating a key store for testing in key management. To create the key store for testing, you can use a command resembling the following. When using JDK 11 or above, you may get the following warning when using the command here. In this case, probably you want to make sure the key pass and store pass values match. The warning is the warning default different store and key passwords not not supported for PKC S12 key stores. Ignoring user specified ignoring user dash specified dash key pass value. Put the server.jks file in the class path, for instance, and then in your bootstrap.yml for config server, create the following settings. Now we are considering using multiple keys and key rotations. If you have configured the key store encrypt.keystore.location and the default locator looks for keys with alias supported by key prefix with the cipher text like resembling in the following. In addition to the curly brace cipher close curly brace prefix in the encrypted property values, the config server looks for 0 or more name value prefixes before the start of the base 64 encoded ciphertext. These keys are passed to text encryptor locator, which can do whatever logic it needs to locate the text encryptor for the cipher. If you have configured the key store encrypt.keystore.location, the default locator look for keys with alias supplied by the key prefix with the ciphertext resembling the following. The locator looks for key names for a key named test key. A secret can also be supplied by using open curly brace secret colon etc closing curly brace value in the prefix. However, it is not supplied. However, if it is not supplied, the default is to use the key store password, which is what you get when you build a key store and do not specify a secret. If you do supply a secret, you should also encrypt the secret by using a custom secret locator. When the keys are being used only to encrypt a few bytes of configuration data, that is, when they are not being used elsewhere, the key rotation is hardly ever necessary to encrypt on cryptographic grounds. However, you might occasionally need to change the keys, for example, in the event of a security breach. In that case, all clients would need to change their source config files, for example, in Git, and use a new key colon etc. prefix for all the ciphers. Note that the client need to first check that the key alias is available in the config server key store. If you want to let the config server handle all encryption as well as decryption, name :value prefixes can also be added to as plain text posted to the /encrypt endpoint. Now we are considering serving encrypted properties. Sometimes you want the client to decrypt the configuration locally instead of doing it in the server. In that case, if you provide the encrypt .asterisk configuration to locate a key, you can still have the /encrypt and /decrypt endpoint, but you need to explicitly switch off the decryption of outgoing properties by placing spring.cloud.config.server.encrypt.enabled equal false in bootstrap.yml or properties. If you do not care about these endpoints, it should work if you do not configure either the key or enabled flag. Now we are considering serving alternative formats. The YAML and properties representations have an additional flag provided as a Boolean query parameter called resolved placeholders to signal that placeholders in the source documents in the standard Spring $ curly open curly brace etc. closing curly brace form should be resolved in the output before rendering where possible. The default JSON format from the environment endpoint is perfect for consumption by Spring application because it's mapped directly onto environment abstraction. If you prefer, you can consume the same data as YAML or Java properties by adding the suffix .yml or .properties to the resource path. This can be useful for consumption by applications that do not care about the structure of the JSON endpoint or extra metadata they provide. For example, an application that is not using Spring might benefit from simplicity of this approach. The YAML and properties representation have additional flag provided as a Boolean query parameter called resolved parameter. Resolved placeholders to signal that placeholder in the source document should be resolved in the output before rendering where possible. This is useful feature for consumers that do not know about Spring placeholder conventions. There are limitations by using YAML or properties formats, mainly in relation to the loss of metadata. For example, JSON is structured as an ordered list of property sources with names that correlate with the source. The YAML and properties forms are coalescent into a single map, even if the origin of the values has multiple sources and the names of the original source files are lost. Also, the YAML representation, not necessarily a faithful representation of the YAML source in backing repository either. It is constructed from a list of flat property sources, and assumptions have to be made about the form of the keys. Now we are considering JIT, SVN and native backends in serving plain text. The /sample /default /master /nginx.config resource might be as follows. Consider the following example for JIT or SVN repository or native backend. The application.yml and nginx config. The nginx config the nginx.config might resemble the following listing. Application.yml might resemble the following listing. The /sample /default /master /nginx.config resource might be as follows. /sample /development /master /nginx.config might be as follows. Now we are considering embedding the config server when setting spring dot cloud dot config dot server dot bootstrap to true. You must also use the composite environment repository configurations. For example, here the config server runs best as a standalone application. However, if need be, you can embed it in another application. To do so, use at enable config server annotation, an optional property named spring.cloud.config.server.bootstrap can be useful in this case. It is a flag to indicate whether the server should configure itself from its own remote repository. By default, the flag is off because it can delay startup. However, when embedded in another application, it makes sense to initialize the same way as any other application. When setting spring.cloud.config.server.bootstrap to true, you must also use a composite environment repository configuration. If you use bootstrap flag, the config server needs to have its name and repository URI configured in bootstrap.yml. To change the location of the server endpoint, you can optionally set the spring.cloud.config.server.prefix. It's not here. For example, /config to serve and resource under a prefix. Prefix should start but not end with /. It is applied to at request mappings in the config server, that is underneath the Spring Boot server.path and server.context path prefixes. If you want to read the configuration for an application directly from the backend repository instead of the config server, you basically want an embedded config server with no endpoints. You can switch off the endpoints entirely by not using an at enable config server annotation and set spring.cloud.config.server.bootstrap to true or equal true. Now we are considering push notification and Spring Cloud Bus. If you add dependency on your Spring Cloud config monitor library and activate the Spring Cloud Bus in your config server, then a /monitor endpoint is enabled. Many source code repository providers such as GitHub, GitLab, GT, Gogs or Bitbucket notify a few of changes in a repository through a webhook. You can configure the webhook through the provider's user interface as a URL and set the events in which you are interested. For instance, GitHub uses post to the webhook in a JSON body containing a list of commits and a header. GitHub event set to push. If you add a dependency on the Spring Cloud config monitor library and activate Spring Cloud Bus in your config server, then a /monitor endpoint is enabled. When a webhook is activated, the config server sends refresh remote application event targeted at applications it thinks might have changed. The change detection can be strategized. However, by default, it look for changes in files that match the application name. For example, foo.properties is targeted at foo application, while the application.properties is targeted at all applications. The strategy to use when you want to override the behavior is property path notification extractor, which accepts the request headers and body as parameters and returns a list of file paths that change. The default configuration work out of the box with GitHub, GitLab, GT, Jogs and Bitbucket. In addition to the JSON notification from GitHub, GitLab, GT or Bitbucket, you can trigger the change notification by posting to /monitor with form encoded body parameters with the pattern of path equal application. Doing so broadcasts to application matching application patterns which can contain wildcards. Note the refresh remote application event is transmitted only if the Spring Cloud bus is activated in both config server and in the client application. The default configuration also detects file system changes in local Git repositories. In that case, the webhook is not used. However, as soon as you edit a config file, the refresh is broadcast. Now we are considering AOT and native image support. Implementing native image support is blocked by Graal 5134, and we like to require the completion of the work on here the http /github.com/graalvm/taming build time initialization to be fixed. The Spring Boot application can take immediate advantage of Spring. Since 4.0.0 Spring Cloud Config Server supports Spring AOT transformations. However, for the time being, Graal VM native images are not supported. So implementing native image support is blocked by Graal 5134, and we like to require the completion work on this web address. You can see the web address to be fixed. This is the address https://github.com/graalvm/taming build time initialization. You can go visit the address and check it. So as an exception example, we can consider environment exception, class environment exception. This is in the package org.springframework.cloud.config.server.environment. As an error example, we can consider this error occurred in the environment Spring Cloud Config Server and HTTPS JIT backend via a proxy. Here you can see clouds config report.jit. You can see org.springframework.cloud.config.server.environment, etc. Now we are focusing on service registry. Here you can see service registry. Service registry provides your apps with the implementation of a service discovery pattern. One of the key tenets of a microservice-based architecture. Trying to hand configure each client of a service or adapt some form of access convention can be difficult and prove to be brittle in production. Instead, your apps can use the service registry to dynamically discover and call registered services. When a client registers with the service registry, it provides a metadata about itself, such as its port, its host and ports. The registry expects a regular heartbeat message from each service instances. If an instance begins to consistently fail to send the heartbeat, the service registry will remove the instance from its registry. Service registry is based on Eureka, Netflix service discovery server and client. Here producers are connected to service registry through register. and then service registry is connected to consumer through discover, and consumer is connected to producers through connect. Here you can see a server-side discovery pattern. The client makes a request to a service via a load balancer. The load balancer queries the service registry and routes each request to an available service instance. As with the client-side discovery, service instances are registered and deregistered with the service registry. The AWS Elastic Load Balancer (ELB) is an example of a server-side discovery router. ELB is commonly used to load balance external traffic from internet. However, you can also use ELB to load balance traffic that is internal to a virtual private cloud (VPC). A client makes a request HTTP or TCP via ELB using its DNS name. ELB load balances the traffic among a set of registered Elastic Compute Cloud (EC2) instances or EC2 container service ECS containers. There isn't a separate service registry. Instead, EC2 instances and ECS containers are registered with the ELB itself. HTTP servers and load balancers such as Nginx Plus and Nginx can also be used as a server-side discovery load balancer. Some deployment environments such as Kubernetes and Marathon run a proxy on each host in a cluster. The proxy plays a role of a server-side discovery load balancer. In order to make a request to a service, the client routes the request via the proxy using host IP address and the service assigned port. The proxy then transparently forward the request to an available service instances running somewhere in the cluster. Server-side discovery pattern has itself benefits and drawbacks. The one great benefit of this pattern is that the details of discovery are abstracted away from the client. Client simply makes request to the load balancer. This eliminates the need to implement discovery logic for each programming language and frameworks used by your service clients. Also, as mentioned before, some deployment environments provide this functionality for free. This pattern also has some drawbacks. However, unless the load balancer is provided by the deployment environment, it is yet another highly available system component that you need to set up and manage. The service registry. The service registry is the key part of the service discovery. It is a database containing a network locations of service instances. A service registry needs to be highly available and up to date. Clients can cache network locations obtained from the service registry. Consequently, a service registry consists of cluster servers that use a replication protocol to maintain this consistency. Netflix Eureka is good example of service registry. It provides the REST API for registering and querying service instances. A service instance registers its network location using a POST request. Every 30 seconds, it must refresh its registration using put request. A registration is removed by either using an HTTP delete request or by the instance registration timeout. As you might expect, a client can retrieve the registered service instances by using HTTP GET requests. Netflix achieved high availability by running one or more Eureka servers in each Amazon EC2 availability zone. Each Eureka server runs on EC2 instance that has an elastic IP address. DNS text records are used to store the Eureka cluster configuration, which is a map of availability zones to a list of network locations of Eureka servers. When a Eureka server starts up, it queries DNS to retrieve a Eureka cluster configuration, locates its peers, and assigns itself an unused elastic IP address. Eureka client service and service clients query DNS to discover network locations of Eureka servers. Clients prefer to use a Eureka server in the same available zone. However, if none is available, client uses Eureka server in another availability zone. Other examples of service registries include etcd, a highly available distributed consistent key value store that is used for shared configuration and service discovery. Two notable projects that use etcd are Kubernetes and CloudFoundry. Console, a tool for discovering and configuring services, is provide an API that allows client to register and discover services. Console can perform health checks to determine service availability. Apache Zookeeper, a widely used highly performance coordination service for distributed applications. Apache Zookeeper has originally a sub-project of Hadoop, but it's now a top-level project. Also, as noted, also some systems such as Kubernetes, Marathon, and AWS do not have an explicit service registry. Instead, the service registry is just a built-in part of its infrastructure. Here, the service instance A is connected to load balancer through request. Load balancer is connected to service registry through query. Load balancer is connected to here REST to REST API through load balance and load balance. Service instances are connected to service registry through register. Here you can see the IP addresses here, and here service instance is connected to REST API and client registry. The client registry is connected to service registry through register. Here you can see service instance A, service instance B, service instance C. Now you can see self-registration pattern here. When using a self-registration pattern, a service instance is responsible for registering and deregistering itself with the service registry. Also, if required, a service instance send a heartbeat request to prevent its registration from expiring. This diagram shows the structure of this pattern. A good example of this approach is the Netflix OSS Eureka client. The Eureka client handles all aspects of service instance registration and deregistration. The Spring Cloud project, which implement various patterns including service discovery, makes it easy to automatically register a service instance with Eureka. You simply annotate your Java configuration class with @enable Eureka client annotation. The service registration pattern has various benefits and drawbacks. One benefit is that is relatively simple, and it doesn't require any other system components. However, the major drawback is that it couples the service instances to the service registry. You must implement the registration code in each programming language and framework used by your services. Alternative approach which decouples services from the service registry is the third-party registration pattern. Here you can see a REST API is connected to service instance A. You can see the IP address and the port here. Service instance A is connected to service registry through register, service name, IP address and the port here, and heartbeat and unregister is here also. Here you can see a third-party registration pattern. When using the third-party registration pattern, service instances aren't responsible for registering themselves with service registry. Instead, another system component known as service registrar handles the registration. The service registrar tracks the changes to the set of running instances by either polling the deployment environment or subscribing it to events. When it notices the newly available service instance, it registers the instance with the service registry. The service registrar also deregisters terminated services instances. This diagram shows the structure of this pattern. One example of service registrar is the open source registrar project. It automatically registers and deregisters service instances that are deployed as Docker containers. Registrar supports several service registries, including etcd and console. Another example of service registrar is Netflix OSS Prana, primarily intended for services written in non-JVM languages. It is a sidecar application that runs side by side with a service instance. Prana registers and deregisters the service instance with Netflix Eureka. Service registrar is a built-in component of deployment environments. The EC2 instances created by an auto-scaling group can be automatically registered with ELB. Kubernetes services are automatically registered and made available for discovery. Third-party registration pattern has various benefits and drawbacks. A major benefit is that services are decoupled from the service registry. You don't need to implement service registration logic for each programming language and the framework used by your developers. Instead, the service instance registration is handled in a centralized manner with a dedicated service. One drawback of this pattern is that unless it's built into the deployment environment, it is yet another highly available system component that you need to set up and manage. Here, service instance A is connected to REST API. Here you can see the IP address and port. Service instance A is connected to service registry. Registrar is connected to service instance A here through health check, and register is connected to service registry through register service name and here IP address and the port and heartbeat, and also disconnect through unregister. Here you can see inter microservice communication via Eureka. Imagine a scenario in which microservice A is trying to invoke microservice B. Microservices do not maintain hard-coded network locations for communication. The following figure illustrates how microservice A uses Eureka to obtain the network location of service B and make a request. Step 1 here, service A and service B registers in Eureka server, providing their application names and network locations. Service A intends to access service B, therefore it possesses the application name, not the network location of service B. Step 3, service A presents the application name of the service B to Eureka server and obtains the corresponding network location. Service A uses step 4, service A uses the obtained network location of the service B to make a request via HTTP or some other protocol. Here the service A is connected to a Eureka server via registers in Eureka app name service A here, and here service B is connected to Eureka server via registers in Eureka app name service B, and here the service A is connected to Eureka server via presenting the service B application name, and Eureka server is connected to service A via obtaining the network location of service B, and service A is connected to service B via invoking service B with IP address and port number obtained via Eureka server. As an example, we can consider interface service registry or extend registration, contract to register and deregister instances with the service registry. This is in the package org.spring framework.cloud.client.service registry. As an example 2, we are considering service registration and discovery. Start a Eureka here we are considering start a Eureka service registry now. The following listing from eureka-service/main/java/com.example.service registration and discovery service /registration service registration and discovery service application.java shows the service application. The annotation type enable Eureka server annotation to activate Eureka server and related configuration Eureka server auto configuration. This is in the package org.spring framework.cloud.netflix.eureka.server. You first need a Eureka service registry. You can use the Spring's clouds at enable Eureka server to stand up a registry with which other applications can communicate. This is a regular Spring Boot application with one annotation at enable Eureka server added to enable the service registry. The following listing is from this location. Shows the service application. When the registry starts, it will complain with the stack trace that there are no replica nodes to which the registry can connect. In a production environment, you will want to more than one instance of the registry. For our simple purposes, however, it suffices to disable the relevant logging. It's a good convention to put this registry on a separate port when using it. Add some properties to eureka-service/src/main/resources/application.properties to handle all of these requirements, as the following listing shows. Now we are considering talking to the registry. Now that you have started a service registry, you can stand up a client that both registers itself with the registry and uses Spring Cloud Discovery Client abstraction to interrogate the registry for its own host and port. The @enable discovery client activates the Netflix Eureka Discovery Client implementation. There are other implementations for other service registers such as HashiCorp's console or Apache Shoekeeper. The following listing is from eureka-client src/main/java/example/service registration and discovery clients /service registration and discovery client application.java. Shows the client application here. Whatever implementation you choose, you should soon see the eureka-client registered under whatever name you specify in the spring.application.name property. This property is used a lot in Spring Cloud, often in the earliest phases of service configuration. This property is used in Service Bootstrap, and by convention it lives in eureka-client/src/main/resources/bootstrap.properties, where it is found before src/main/resources/application.properties. The following listing shows the bootstrap.properties file. The eureka-client defines a Spring MVC REST endpoint service instance REST controller that returns the enumeration of all registered service instances at http://localhost:8080/service-instances/service-beautiful-client. Now we are considering test the application. Test the end-to-end result by starting the Eureka-service first, and then once that has loaded, starting the Eureka client. To run the Eureka service with Maven, run the following command in a terminal in the /complete directory in this example. To run the Eureka client with Maven, run the following command in a terminal window in the /complete directory in this example. To run the Eureka service with Gradle, run the following command in a terminal window in the /complete directory in this example. To run the Eureka client with Gradle, run the following command in a terminal window in the /complete directory in this example. The Eureka client, Eureka-client will take about a minute to register itself in the registry and to refresh its own list of registers instances from the registry. Visit the Eureka client in the browser at http://localhost://service-instances-a-beautiful-client in this example. There you should see the service instance for the Eureka-client reflected in the response, and if you see an empty list element, wait a bit and refresh the page. Now we are considering service registry. The following example shows the service registry in use. The interface service registry or extends registration, contract to register and deregister instances with the service registry. This is in the package org.springframework.cloud.client.service-registry. Commons now provide a service registry interface that provides methods such as register, registration, and deregister registration, which lets you to provide custom registered services. Registration is a marker interface. The following example shows service registry. Each service registry implementation has its own registry implementation. Zookeeper registration is used with Zookeeper service registry. Eureka registration is used with Eureka service registry. Console registration used with console registry. If you are using service registry interface, you are going to need to pass the correct registry implementation for the service registry implementation you are using. Call through some external process such as an event or a custom actuator endpoint. Now we are considering service registry auto registration. To disable that behavior, you can set * at enable the discovery client auto register equal false to permanently disable auto registration. Annotation type enable discovery client. Annotation to enable a discovery client implementation. org.springframework.cloud.client.discovery. This is in the package org.springframework.cloud.client.discovery. The optional element public abstract boolean auto register. If true, the service registry will automatically register the local server. By default, service registry implementation auto register the running service. You can use the spring.cloud.service.registry.auto-configuration.enabled equal false to disable the behavior through configuration. Now we are considering service registry activator endpoint. Spring Cloud Commons provides /service-registry activator endpoint. This endpoint relies on a registration bean in this Spring application context, calling /service-registry with the get returns the status of the registration. Using post to the same endpoint with the JSON body changes the status of the current registration to the new value. The JSON body has to include the status field with the preferred value. Please see the documentation of the service registry implementation you use for the allowed values when updating the status and the values returned for the status. For instance, Eureka supported status are up, down, out of service, and unknown. Now we are considering Spring Cloud Zookeeper and service registry. The service instance registration class offers a builder method to create registration objects that can be used by the service registry as shown in the following example. Spring Cloud Zookeeper implements service registry interface, letting developers register arbitrary services in a programmatic way. Now we are considering instance status in Spring Cloud Zookeeper and service registry. To change the status of the instance, make a post request with out of service to the service registry. Instance status actuator endpoint as shown in the following example. Netflix Eureka supports having instances that are out of service registered with the server. These instances are not returned as active service instances. This is useful for behaviors such as blue-green deployment. Note that the curator service discovery receipt does not support this behavior. Taking advantage of the Netflix payload has let Spring Cloud Zookeeper implement out of service by uploading some specific metadata and then filtering on the metadata with the ribbon Zookeeper servlet list. The Zookeeper servlet the Zookeeper server list filters out all null instances statuses that do not equal up. If the instance status field is empty, it is considered to be up for backward compatibility. To change the status of an instance, make a post with out of service to the service registry. instance status actuator endpoint as shown in the following example. This preceding example uses the HTTP command from https://httpie.org. Now we are considering service registry configuration. If no scheme is configured and the service is not exposed as a secure service, then the configuration default to Spring Cloud vault.scheme, which is HTTPS when it's not set. You can use a discovery client such as from Spring Cloud console to locate a vault server by setting cloud.vault.discovery.enable equal true, default false. The net result of that is that your app needs a bootstrap.yml or an environment variable with appropriate discovery configuration. The benefit is that the vault can change its coordinates, and as long as the discovery service is fixed, is a fixed point, the default service ID is vault, but you can change that on the client with spring.cloud.vault.discovery.service-id service ID. The discovery client implementations all support some kind of metadata map. For example, for Eureka, we have eureka.instance.metadata map. Some additional properties of the service may need to be configured in its service registration metadata so that clients can connect correctly. Service registries that do not provide details about transport layer security need to provide the scheme metadata entry to be set either to HTTPS or HTTP. If no scheme is configured and the service is not exposed as secure service, the configuration details defaults to spring.cloud.vault.scheme, which is HTTPS when it's not set. As an error example, we can consider this. The fail to introspect annotations on class org.springframework.cloud.netflix.eureka.config.eureka discovery client.config service bootstrap configuration. Java.lang.illegal state exception could not obtain annotation attribute value for public abstract, etc. Now we are focusing on circuit breaker dashboard. Circuit breaker dashboard provides Spring apps with an implementation of the circuit breaker pattern. Cloud native architectures are typically composed of multiple layers of distributed services. End user request may comprise multiple calls to these services, and if a lower level service fails, the failure can cascade up to the end user and spread to other dependent services. Heavy traffic to a failing service can also make it difficult to repair. Using circuit breaker dashboard, you can prevent failures from cascading and provide fallback behavior until a failing service is restored to normal operation. Distributed systems can be unreliable. Requests might encounter timeouts or fail completely. A circuit breaker can help mitigate these issues, and Spring Cloud Circuit Breaker gives you the choice of three popular options: Resilience 4J, Sentinel, or Hystrix. Here you can see a circuit breaker dashboard. Circuit breaker dashboard provides Spring apps with an implementation of the circuit breaker pattern. Cloud native architectures are typically composed of multiple layers of distributed services. End user requests may comprise multiple calls to these services, and if a lower level service fails, the failure can cascade up to the end user and spread other dependent services. Heavy traffic to a failing service can also make it difficult to repair. Using circuit breaker dashboard, you can prevent failures from cascading and provide fallback behavior until the failing service is restored to a normal operation. When applied to service, a circuit breaker watches for failing calls to the service, and if failures reach certain threshold, it opens the circuit and automatically redirect to the calls through a specific fallback mechanism. This gives the failing service time to recover. Here you can see a closed on-call pass-through, call succeed, reset count, call fails, count failure, threshold reached, trip breaker. Closed is connected to open through trip breaker. On-call fail, on timeout attempt reset. Open is connected to half open through attempt reset. Here the on-call pass-through, call succeed reset, call fails trip breaker. Half open is connected to open through trip breaker, and open is connected to half open through attempt reset, and here half open is connected to close through reset. Here you can see historic fallbacks prevent cascading failures. A service failure in a lower level of services can cause cascading failures all the way up to the user. When the calls to a particular service exceed circuit breaker.request volume threshold default to 20 requests, and the failure percentage is greater than circuit breaker.error threshold percentage default to over 50%, in a rolling window defined by metrics rolling stats time in milliseconds default to 10 seconds, the circuit opens and circuit opens and the call is not made. In case of error and an open circuit, the fallback can be provided by the developer. Having an open circuit stop cascading failures and allows overwhelmed or failing services time to recover. The fallback can be another historic protected call, static data, or sensible empty value. Fallbacks may be chained so that the first callback makes some other business call, which in turn falls back to static data. Here you can see API is connected to browser, mobile, and mobile. Here you can see the API is connected to service A, fallback, service C, service D, and service C. And here you can see service B is failed. Here you can see a historic dashboard. Microservice graph. Netflix has created a library called Historic that implements the circuit breaker pattern. In a microservice architecture, it is common to have multiple layers of service call as shown in here. And here you can see a microservice graph here. Historic stream sample apps. As an example, here we are considering apply circuit breaker pattern in a Spring Cloud circuit breaker. let's create a new service that uses this interface to make API calls to the bookstore application. Here the interface reactive circuit breaker, Spring Cloud reactive circuit breaker API. This is in the package org.springframework.cloud.client.circuitbreaker. Now we are considering set up a server microservice application. Here the bookstore service will have a single endpoint. It will be accessible at /recommended, and will for simplicity return mono of string recommended reading list. Edit our main class in here the bookstore application.java. It should look like this. The @REST-controller annotation marks bookstore application as a controller class, like @controller does, and also ensures that request mapping methods in this class will behave as though annotated with @response body. That is, the return value of request mapping methods in this class will be automatically converted appropriately from their original types and will be written directly to the response body. We are going to run this application locally alongside a client service application. So in here in src/main/resources/application.properties, set the server.properties server.port so that the bookstore service won't conflict with the client when we get that running. So set the server.port equal 8090 in application.properties file. Now we are considering set up the client microservice application. Reading application will be our front end, so it were to the bookstore application, and we will be able to view our reading list there at /2-read and that reading list will be retrieved from the bookstore service application. To get this list from bookstore, we are using Spring web client class. The web client makes the HTTP get request to the bookstore service URL as we provide it, and then returns the result as a mono of string. Add the server.port property to src/main/resources/application.properties. At this line, server.port equals 8080. We now can access in a browser the /read endpoint in our reading application and see our reading list. Yet since we rely on the bookstore application, if anything happens to it, or if reading is simply unable to access bookstore, we will get no list, and our users will get a nasty HTTP 500 error message. Now we are considering apply circuit breaker pattern. Spring Cloud circuit breaker library provides an implementation of the circuit breaker pattern. uh, when we wrap a method call in a circuit breaker, Spring Cloud circuit breaker watches for falling calls to that method, and if it fails, build up threshold. Spring Cloud circuit breaker open up the circuit so that subsequent call will automatically fail. While the circuit is open, Spring circuit breaker redirect calls to the method, and they are passed to our specific fallback method. Spring Cloud circuit breaker supports many different circuit breaker implementation, including Resilience 4, Historic, Sentinel, and Spring Retry. This guide we will use Resilience 4J implementation. To use Resilience, to use this implementation, we just need to add Spring-Cloud-Starter-Circuit Breaker-Reactor-Resilience 4J to our application's class path. Spring Cloud Circuit Breaker provides an interface called Reactive Circuit Breaker Factory, which we can use to create new circuit breakers for our application. An implementation of this interface will be auto-configured based on the starter, and that is on our application's class path. Let's create a new service that uses this interface to make API calls to bookstore application. The reactive circuit breaker factory has a single method called create. We can use to create new circuit breakers. Once we have our circuit breaker, we will we all have to do is call run takes a mono of flux and an optional function. The optional function parameter acts as our fallback for of anything that goes wrong. In our sample here, the fallback will just return mono containing the string cloud native Java orally. With our new service in place, we can update code in reading application to use the new service. Here's the reading src cd reading /src /main/java /hello /reading application.java. Now try it out. Run both the bookstore service and the reading service, and then open a browser to the reading service at localhost colon 8080/2-read. Reading services here. forward slash localhost colon 8080 forward slash 2 dash read, and you should see the complete recommended reading list. Now shut down the bookstore application. Our list source list source is gone now, but thanks to history and Spring Cloud Netflix, we have a reliable abbreviated list to stand in the gap. You should see Cloud Native Java or really Cloud Native Java really here. Now we are, as an example too, we are considering default configuration in configuring resilience for circuit breakers. The configure default method can be used to provide the default configuration. The class resilience for circuit breaker factory is in the package org.springframework.cloud.circuitbreaker.resilience4j. To provide default configuration for all of your circuit breakers, create customize bean that is passed resilience for circuit breaker factory, or reactive resilience for circuit breaker factory. The default the configure default method can be used to provide the default configuration. Here you can see the reactive example. Now we are considering a default configuration in Spring retry circuit breakers. The configure default method can be used to provide the default configuration. To provide the default configuration for all of your circuit breakers, create customizer bean that is passed Spring retry circuit breaker factory. The configure default method can be used to provide the default configuration. Now we are considering how to include historics in history clients in circuit breaker. The following example shows a minimal Eureka server with historic circuit breaker. The annotation type enable circuit breaker deprecated as of the 3.0.1 release. Historic has been removed from Spring Cloud Netflix, and it was the only implementation using this annotation. This is in the org.springframework.cloud.client.circuit breaker. To include historic in your project, use start with the group ID of org.springframework.cloud and artifact ID of spring-cloud-starter-netflix-historics. Following example shows a minimum Eureka server with historics circuit breaker. The @historic command is provided by Netflix contrib library called Javanica. Spring Cloud automatically wraps the Spring beans with that annotation in a proxy that is connected to the historic circuit breaker. The circuit breaker calculates when to open and close the circuit and what to do in the case of failure. Configure @historic command. To configure @historic command, you can use the command properties attribute with the list of @historic property annotations. Do stuff that might fail. Something useful here. As an example 5, we are considering propagating security context or using Spring scopes. Following example demonstrates setting the thread in an annotation. The annotation type historic command. This annotation used to specify some methods which should be processed as historic commands. This is in the package com.netflix.historic.contrib.javanica.annotation. If you want some thread local context to propagate into historics command, @historic command, the default declaration does not work because it executes the command in a thread pool in case of timeouts. You can switch historic to use the same thread as the caller, though through configuration or directly in the annotation by asking it to use a different isolation strategy. The following example demonstrates setting the thread in the annotation. The same thing applies if you are using session scope or @request scope. If you encounter a runtime exception that says it cannot find the scope context, you need to use the same thread. You also have the option to set historic.share security context property to true. Doing so auto configures a historic concurrency strategy plugin hook to transfer security context from your main thread to the one used by the historic command. Historic does not let multiple historic concurrency strategies be registered as an extension mechanism is available by declaring your own historic concurrency strategy as a Spring bean. Spring Cloud looks for your implementation within Spring context and wrap it inside its own plugin. Now we are considering health indicator. The state of the connected circuit breakers are also exposed in the health endpoint of the calling application as shown in the following example. Now we are considering a historic metrics stream. So doing so exposes the /actuator /historic.stream as a management endpoint as shown in the following example here. To enable historic metrics stream, include a dependency on Spring Boot start actuator and set management.endpoints.web.exposure.include historic.stream stream. Doing so exposes /actuator /historic.stream as a management endpoint as shown in the following example here. Now we are considering replicating the circuit breaker dashboard in replacing the Spring Cloud Services circuit breaker dashboard. In order to enable these metrics to be sent through micrometer, the following properties have to be added in the client application. By default, the circuit breaker dashboard has a histogram here for the 19th and 99th and 99.5th percentiles. In order to enable those metrics to be sent through micrometer, the following properties have to be added in the client application. With the percentiles histogram enabled, we will have access to each pi we have set as properties. Now we are considering deploy your application to Azure. In use circuit breaker dashboard with Azure Spring Apps. To these apps, do not use config server, so there is no need to set up config server for Azure Spring Apps. Create and deploy as follows. In verify your apps, after all apps are running in and discoverable, access user service with the path http username dash user dash service dot azure microservices.io /personalized/1 from your browser in this example. If the service can access recommendation dash service, you should get the following output. Refresh web page a few times if it doesn't work. In access your historic dashboard and metrics team here, using public endpoints, access historic turbine with the path https // service name dash historic dash turbine dot azure microservices.io /historic from your browser, and then copy the turbine stream URL https // service name dash historic dash turbine dot azure microservices.io /turbine dot stream cluster equal default into the text box, and then select monitor stream. This will display the dashboard. If nothing shows in the viewer, hit the user service endpoints to generate streams. Now you can experiment with the circuit breaker dashboard. Note: in production, history dashboard and metrics stream should not be exposed to the internet. As an exception example, we can consider the class not fallback available exception, a runtime exception that tells no fallback is available for the circuit breaker. This is in the package org.springframework.cloud.client.circuit As an error example, we can consider this error occurred in the in failing to provision a circuit breaker dashboard from Spring Cloud Services 2.0.2. Status create failed. Message error creating service instance java.lang.illegal argument exception. So service plan standard not found and started and updated here. Now we are considering Spring Cloud Sleuth. Spring Cloud Sleuth implements a distributed tracing solution for Spring Cloud. Here you can see how span and trace look in a system together with Simkin annotations. With terminology, Spring Cloud borrows Dapper's terminology and span. The basic unit of work, for example, sending an RPC is an new span, as is sending responsible for RPC. Spans are identified by a unique 64-bit ID for the span and another 64-bit ID for the trace, and trace the span as part of. Spans also have other data such as descriptions, timestamps, events, key value annotations, tags, the ID of the span that caused them, and process ID is normally IP address. Span can be started and stopped, and they keep track of their timing information. Once you create a span, you must stop it at the same point in the future. The initial span that start trace is called root span. The value of ID of that root span is equal to the trace ID. Trace, a set of spans forming a tree-like structure. For example, if you run a distributed big data store, the trace might be formed by a put request. Annotation, used to record the existence of an event in time. With Brave instrumentation, we no longer need to set a special event for Zipkin to understand who the client and server are. Where the request is started and where it is ended. For learning purpose, however, we mark these events to highlight what kind of an action took place. Client CS, client send, the client has made the request. This annotation indicates the start of the span. SR, server received, the server side got the request and started processing it. Subtracting the CS timestamp from this timestamp reveals the network latency. server sent or SS server sent annotated upon the completion of request processing when the response got sent back to the client, subtracting the subtracting the SR timestamp from this timestamp reveals the time needed by the server side to process the request. CR client received signifies the end of the span. Client has successfully received the response from the server side, subtracting CS timestamp from this timestamp reveals the whole time needed by the client to receive the response from the server. The following image shows how spam and trace look in a system together with Zipkin annotations. Each color of a knot signifies a spam, where there are 7 spams. From A to G. Consider the following knot: trace ID equal X, span ID equal D, client sent. This note indicates that the span has trace ID set to X and span ID set to D, and also the client send event took place. Here you can see service 1, service 2, service 3 and service 4. Here you can see the request is sent to request is connected to service 1. You can see that no trace ID, no span ID, and here trace ID equal X, span ID equal A, and server received. Here you can see the service 1 is connected to service 2 through request. Here trace ID X and span ID B, client sent, and here trace ID X and span ID B, server received. Here you can see trace ID X and span ID C. Here service 2 is connected to service 3 through request. Here you can see trace ID X, span ID D, and client sent, and here trace ID X, span ID D, server received. Here you can see trace ID X, span ID E, and here you can see trace ID X, span ID E, and here you can see trace ID X, span ID D, and server sent. Here service 3 is connected to service 2 through response. Here you can see trace ID X and span ID D, and client received. Here service 2 is connected to service 4 through request. Here you can see trace ID X, span ID F, client sent, and trace ID X, span ID F, server received. Here you can see trace ID X, span ID G, and here you can see trace ID X, span ID G, and here you can see trace ID X, span ID F, server is sent, and here you can see trace ID X, span ID F, and client received. Here service 4 is connected to service 2 through response. Here you can see trace ID X, span ID C, and here you can see trace ID X, span ID D, B, and server is sent. Here service 2 is connected to service 1 and through response. Here you can see trace ID X, span ID B, and client received. Here you can see trace ID X, span ID A, and client sent, and here service is sending a response. Service 1 is sending a response. Here you can see trace ID X and span ID A. Here you can see how parent-child relationship of spans look. Here span ID A and parent ID null is connected to span ID B and parent ID A. This is connected to span ID C and parent ID B, and this is connected to span ID D and parent ID C, and this is connected to span ID E and parent ID D, and here this is connected to span ID F and parent ID C, and this is connected to span ID G and parent ID F. Here you can see a distributed tracing with Zipkin. This example has 7 spans, and if you go to traces, if you go to traces, this in Zipkin you can see this in you can see this number in the second trace as shown in this following image. However, if you pick a particular trace, you can see 4 spans as shown in the following image. When you pick a particular trace, you see merge spans. That means that if there were 2 spans sent to Zipkin with server received and server sent, or client received and client sent annotations, they are presented as a single span. Why there is a difference between 7 and 4 spans in this case? One spans come from HTTP :/start span. It has server received SR and server sent SS annotations. 2 spans come from the RPC call from service 1 and service 2 to the HTTP :/foo endpoint. Server sent and server received events took place in the service 1 side. Server received and server sent events took place on the service 2 side. These 2 spans form one logical span related to an RPC call. 2 spans come from RPC calls from service 2 and service 3 to the HTTP :/bar endpoint. Server sent and server received event took place on the service 2 side. Server received and server sent events took place in the service 3 side. These 2 spans are these 2 spans form one logical span related to an RPC call. 2 spans come from RPC call from service 2 to service 4 to the HTTP :/bus endpoint. The client sent and client received events took place on the service 2 side. Server received and server sent events took place on the service 4 side. These 2 spans form one logical span related to an RPC call. So if we count the physical spans, we have one from HTTP :/start, 2 from service 1 and service 2, and 2 from service 2 calling service 3, and 2 from service 2 calling service 4. In sum, we have total of 7 spans. Logically, we see the information of our 4 total spans because we have one span related to the incoming request to service 1 and 3 span related to RPC calls. Visualizing errors. Zipkin let you visualize errors in your trace. When an exception has thrown and not caught, we set the proper tags on the span, and which Zipkin can then properly colorize. You could see in the list of traces that is red. This appears because an exception is thrown. If you click and trace, you see the similar picture as follows. And here you can see the dependency graph in Zipkin should resemble the following image. So here service 1 is connected to service 2, and service 2 is connected to interact with service 3, service 2 interact with service 4, as an example here. Here you can see when a downstream HTTP call is made, and its trace context is encoded as request headers and along with it, and shown in this. For example, this is regarding propagation. Propagation is needed to ensure activities originating from the same route are collected together in the same trace. The most common propagation approach is copy and trace context from client by sending an RPC request to the server receiving it. For example, the downstream HTTP call is made. The trace context is encoded as request headers and sent along with it, as shown in this following image. The names above are from B3 propagation, which is built into Brave and has implementation in many languages and frameworks. Here you can see trace context is inside client span. Trace ID, parent, span ID, sampled inside trace context here. Trace context context is connected to HTTP headers through extract. Trace context extracts HTTP request headers, XB3 trace ID, XB3 parent span ID, SB3 span ID, XB3 sampled are inside HTTP request headers. HTTP request header injects trace context here, and text context is inside service span, and trace ID, parent span ID and sampled inside trace context here. Here you can see an example of B3 propagation. Here we are considering sharing span IDs between client and server. Normal instrumentation pattern is to create an span representing server side of RPC. Extract might return a complete trace context when applied to an incoming client request. The tracer.join span attempt to continue with this trace using the same span ID if supported, or creating a child spam if not. When the spam ID is shared, the reported data include the flag saying so. Some propagation systems forward only the parent spam ID. When propagation.factory.support join method equal false. In this case, new spam ID is always provisioned, and the incoming context determines the parent ID. Here you can see incoming headers, XB3 trace ID, XB3 parent span ID, XB3 and XB3 span ID are inside incoming headers. Incoming headers are connected to extract trace ID, parent span ID and span ID. Trace ID, parent span ID and span ID are inside trace context. Here you can see join is applied to trace ID, parent span ID, span ID. And here you can see a shared true, and these are inside trace context. Here you can see the example of AWS propagation. Note some spam reporters do not support sharing span IDs. For example, if you set tracing.builder.spam reporter, Amazon X-Ray or Google Stack Drive, you should disable the join by setting tracing.builder.supports join false. Doing so forces a new child spam on tracer.join spam. Here you can see root and parents inside XMS and trace ID, and XMS and trace ID extract trace ID span ID, and trace ID and span ID are inside trace context. Here joins is applied to trace ID and parents span ID here. Parent span ID, trace ID and parent span ID and span ID new are inside trace context here. Here you can see the general architecture of how streaming applications are monitored. The data flow distributed tracing, this is about stream distributed tracing actually, and the data flow distributed tracing architecture is designed around Spring Cloud Sleuth library to provide API for distributed tracing solutions that integrate Open Zipkin Brave. Spring Cloud Sleuth is able to trace your streaming pipeline messages and export the tracing information to an external system to analyze and visualize. Spring Cloud Sleuth support Open Zipkin compatible systems such as Zipkin server or Wavefront distributed tracing. Spring Cloud all Spring Cloud stream applications are pre-configured to support message distributed tracing and exporting to Zipkin server and or Wavefront tracing. The tracing export is disabled by default. Use management.metrics.export.wavefront.enabled equal true and or spring.zipkin.enabled equal true to enable tracing information export to Wavefront or Zipkin server. Consult Spring Sleuth properties for Sleuth configuration properties. The following images shows the general architecture of how streaming applications are monitored. For streaming applications based on Spring Cloud function, prior version 3.1.x and the Spring Cloud Sleuth library leverages the Spring integration for tracing instrumentation. Latter might produce unnecessary noise trace information for some Spring integration internal components. Starting with Spring Cloud Function 3.1 plus, the Spring Cloud Sleuth tracing instrumentation offers a better tailored tracing information for SCF based application. Here you can see a source, processor and sink are connected to Spring Cloud Sleuth. Source is connected to processor is connected to sink, and Spring Cloud Sleuth source, processor and sinks are inside streams here. Local Kubernetes and CloudFoundry. Data flow server is connected to Skipper server, and Skipper server is connected to streams through streams lifecycle management, and Spring Cloud Sleuth is connected to trace collection server through traces, and you can see Zipkin and Wavefront, and trace collection server is connected to traces UI. Here you can see use Zipkin for distributed log analysis. Zipkin is a distributed tracing system. It helps gather timing data needed to troubleshoot latency problems in service architectures. Features include both the collection and lookup of this data. Here you can see microservices are connected to Zipkin distributed logs tracing server through logs with Spring Cloud Sleuth tokens. Zipkin distributed logs tracing service connected to database. Here we are considering spam lifecycle with Spring Cloud Sleuth's API. Spring Cloud Sleuth's core in its API module contains all necessary interfaces to be implemented by a tracer. The project comes with open Zipkin Brave implementation. You can check how traces are bridged to the Sleuth's API by looking at org.springframework.cloud.sleuth.brave.bridge. The most commonly used interfaces are org.springframework.cloud.sleuth.tracer. Using a tracer, you can create a root spam capturing the critical path of a request. org.springframework cloud.sleuth.span. Span is a single unit of work that needs to be started and stopped. Contains timing information and events and tags. You can also use your tracer implementation API directly. Let's look at the following spam lifecycle actions. Start. When you start a span, its name is assigned and start timestamp is recorded. End. The spam gets finished. The end time of the span is recorded, and if the span is sampled, it is eligible for collection, for example to Zipkin. Continue. Then the span gets continued, for example in another thread. Create with explicit parent. You can create a new span and set an explicit parent for it. Spring Cloud Sleuth create an instance for tracer for you. In order to use it, you can auto-wire it. As an example, we can consider package org.springframework.cloud.sleuth. In example 2, we are considering add sleuth, considering Spring boot config. Add sleuth to class path. The artifact ID is Spring Cloud Starter Sleuth. Spring Cloud Starter Sleuth with Brave. as long as Spring Cloud Sleuth is on the class path, any Spring Boot application will generate trace data. Run this app and then hit the home page and you will see the trace ID and span ID populated in logs. If this app calls out another one, for example with REST template, it will send the trace data in headers, and if the receiver is another Sleuth app, you will see the trace continue there. Instead of logging the request in the header explicitly, you could set login.level.org.spring.framework.web.servlet.dispatcher-servlet equal debug. Sleuth defaults to a rate limited sampler. That means it will sample up to 100,000 transactions per second. Set spring.application.name equal bar, for instance, to see the service name as well as the trace and span IDs. Now we are considering writing the code in getting started. By default, Maven compiles sources from src/main/java, so you need to create that directory structure and then add the file name src/main/java/example.java to contain the following code here. To finish our application, we need to create a single Java file. Although there is not too much code there, quite a lot is going on. The REST controller and request mapping annotations. The Spring Boot sets up the REST controller and makes our application bind to a Tomcat port. Spring Cloud Sleuth with Brave Tracer will produce instrumentation of incoming requests. At this point, this is now running the example. At this point, our application should work, since you used to use the spring-boot-starter-parent pom, and you have a useful run goal that you can use to start the application. Type spring_application_name equal backend mven spring-boot:run from the root project directory to start the application. And if you open the web browser to localhost:8080, you should see the hello world here. If you check the logs, you should see a similar output like this. You can notice that logging format has been updated with the following information. Backend 0b6 AAF 642574 EDD3 and 0b6 AAF 642574 EDD3. This entry corresponds to application name, trace ID and span ID. The application name got read from the spring_application_name environment variable. Instead of logging the request in the handler explicitly, you could set login.level.org.springframework.web.servlet.dispatcher-servlet equal debug. To gracefully exit the application, press Ctrl C. Now we are considering creating an ending spans in span lifecycle with Spring Cloud Sleuth in using Spring Cloud Sleuth. You can manually create spans by using tracer as shown in the following example. The class span class for gathering and reporting statistics about a block of execution. This is in the package org.springframework.cloud.sleuth. In this example, we could see how to create a new instance of the span. If there is already a span in this thread, it becomes a parent of the span. Always clean after you create the span. If your span contains a name greater than 50 chars, that name is truncated to 60 chars. Your names have to be explicit and concrete. Big names lead to latency issues and sometimes even exceptions. Start a span. If there was a span present in this thread, it will become a new span parent. You can tag a span. You can log an event on a span. Once done, remember to end the span. This will allow collecting the span to send it to the distributed tracing system, for example, Zipkin. Now we are considering at span name annotation in naming spans. You can name the span explicitly by using at span name annotation as shown in the following example. Annotation type span name. Annotation to provide the name for the span. You should annotate all your custom runnable and or callable classes for the instrumentation logic to pick up how to name the span. This is in the package org.springframework.cloud.sleuth. In this case, when processed in the following manner, the span is named calculate text. Perform logic. Some additional logic here. Now we are considering baggage in Spring Cloud Sleuth features. The following example shows setting baggage values using Spring Cloud Sleuth API. Distributed tracing works by propagating fields inside and across services that connect to the trace together, trace ID and span ID notably. The context that hold these fields can optionally push other fields that need to be consistent regardless of many services are touched. The simple name of these extra fields is baggage. Here you can see the interface baggage in scope, inspired by OpenShipkin Brave baggage field. Since some tracer implementation require a scope to be wrapped around baggage must be closed that the scope does not leak. Some trace implementation make baggage immutable. For example, open telemetry. So when you use when the values get updated, they might create new scope. Others will return the same one. For example, OpenShipkin Brave represent the single baggage entry. This is in the package org.springframework.cloud.sleuth. Sleuth allow you to define which baggage are permitted to exist in trace context, including what header names are used. The following example shows setting baggage values using Spring Cloud Sleuth API. There's currently no limitation of the count of size of baggage items. Keep in mind that too many can decrease system throughput or increase RPC latency. In extreme cases, too much baggage can crash the application due to exceeding transport level, message or header capacity. You can use properties to define fields that have no special configuration, such as name mapping. Spring.sleuth.baggage.remote remote dash fields is a list of header names to accept and propagate remote services. Spring.sleuth.baggage.local dash fields is a list of names to propagate locally. No prefixing applied with these keys. What you set is literally what is used. The name set in either of these properties will result a baggage of the same name. In order to automatically set the baggage values to SLF4J's MDC, you have to set the spring.sleuth.baggage.correlation-fields property with a list of allowed local or remote keys. For example, spring.sleuth.baggage.correlation-fields equal country-code will set the value of the country-code baggage into MDC. Baggage versus tags. Like trace IDs, baggage is attached to messages or requests, usually headers. Tags are key value pairs sent to span to Shipkin. Baggage values are not added span by default, which means that you can't search based on baggage unless you opt in. To make baggage also tags, use the property Spring Sleuth baggage dot tag dash fields, like so. Now we are considering how to set up Sleuth in with Brave in how to guides. Simply add the Sleuth starter to the class path. If you are now we are considering how to make REST template, web client, etc. work. Example where instrumentation will work here. If you are observing that the tracing context is not being propagated, then cause is one of the following. We are not instrumenting the given library. We are instrumenting the library. However, you misconfigured the setup. In case lack of instrumentation capabilities, please file an issue with the request to add such instrumentation. In case of misconfiguration, please ensure that the client you are using to communicate with communicate is a Spring Bean. If you create a client manually via the new operator, instrumentation will not work. Here is the example where instrumentation will work. Here's the example where instrumentation will not work. This will not work because template is not a bean. Now we are considering Apache Kafka in Spring Cloud Sleuth customization. This feature is available for all tracer implementations. We decorate Kafka clients, Kafka producer and Kafka consumer to create a span for each event that is produced or consumed. You can disable this feature by setting the value of spring.sleuth.kafka.enable to false. You have to register producer and consumer as beans in order for Sleuth's auto configuration to decorate them. When you then inject the beans, and expected type must be producer or consumer and not, for example, Kafka producer. We also provide tracing Kafka producer factory and tracing Kafka tracing Kafka producer factory and tracing Kafka consumer factory to be used with Reactor Kafka clients, Kafka sender and Kafka receiver respectively. See an example in the snippet below. Additionally, we decorate any Spring Kafka producer factory and consumer factory available in the context. However, this is disabled if Brave instrumentation is on the class path. Here we are considering seeing the big picture with Zipkin, open Zipkin in distributed tracing with Cloud, Spring Cloud Sleuth and Spring Cloud Zipkin. You may see whatever Spring Cloud stream binding you like, but in this case we will use the Spring Cloud stream RabbitMQ. org.springframework.cloud.colon Spring Cloud start stream RabbitMQ, and here you can see at enable Zipkin stream server. This is org.springframework.cloud.sleuth.zipkin.stream.enable Zipkin stream server. Data collection is a start, but the goal is to understand the data, not just it collect. In order to appreciate the big picture, we need to get beyond individual events. For this, we will use the OpenSipkin project. OpenSipkin is fully open source version of Sipkin, a project that organized or originated at Twitter in 2010 and is based on the Google Dapper papers. Previously, the open source version of Sipkin evolved at a different pace than the version used internally at Twitter. OpenSipkin represents synchronization of those efforts. OpenSipkin is Sipkin, and where we refer to Sipkin in this post, we are referring to the version reflected in OpenSipkin. Sipkin provides a REST API that clients talk to directly. Sipkin even supports a Spring Boot based implementation of this REST API. Using that is as simple as using Sipkin's @enable Sipkin server directly. The Sipkin server delegates rights to the persistence tier via span store. Previously, there is support for using MySQL or an in-memory open span store out of the box. And as an alternative to REST, we can also publish messages to Sipkin server over Spring's Cloud Stream binder like RabbitMQ or Apache Kafka. We will use this option org.springframework.cloud spring cloud sleuth Sipkin streams @enable Sipkin stream server to adapt the incoming Spring Cloud Stream based Sleuth spans into Sipkin spans and then persist them using the span store. You may use whatever Spring Cloud Stream binding you like, but this is the case we will. But in this case, we will use Spring Cloud Stream RabbitMQ org.springframework.cloud Spring Cloud starter stream RabbitMQ. Specify the port in application of properties to pin the Sipkin server to a well-known port so that the UI may later talk to it. Our microservices message client and message service are typical Stream Cloud microservices. Here they only added org.springframework.cloud Spring Cloud Sleuth stream and the appropriate Spring Cloud Stream binder to have their traces published out of band and to Sipkin for analysis. Sipkin web UI makes it easy to analyze and query Sipkin data. You can run the Sipkin web built-in or just grab the latest from the Sipkin project's builds and then run it. When the message service receives a request, it sends a reply message back to message client over Spring Cloud Stream binder, which the client then accepts and logs with Spring integration messaging endpoint. This is a contrived call sequence to demonstrate some of Spring Cloud Sleuth's power. Bring up the UI, then find all recent traces. You can sort by most recent, longest, etc. For finer grained control over which results you see. As an example, we can consider exception example. We can consider this HTTP filter in HTTP server integration in integrations. To disable the filter that logs uncaught exceptions, you can disable the spring .sleuth web exception throwing filter enabled property. As an error example, we can consider this error occurred in the environment with 2021.0.1 Spring Cloud version. Failed to load application context caused by org.spring framework.beans.factory.bean creation exception error creating bean with the name org.spring framework.cloud.sleuth.autoconfig.instrument.web. Skip pattern configuration, etc. Lookup method solution failed, nested exception, etc. This is end of my presentation. Thank you very much for watching it.